Hello, dear finalists. The time is rather critical during your time period. Now, this is a preliminary information. We have not started yet. So you strictly have 10 minutes for your presentation. And we have 10 minutes running. At the 9th minute, if you are not finished yet, you will hear this one. And when it is 10 minutes, it will be, and you should stop. We will start with the Q&A. So please respect the time. This is very important. Thank you. Okay, start. Good afternoon, ladies and gentlemen. Welcome to the 8th Mission Idea Contest final presentation session. I am Ali Rustam Aslan from Istanbul Technical University, Turkey. I'll be moderating the session. And we have 10 presentations. And let me introduce the distinguished members of the jury. On the first row, on the right, Professor Hermann Stein, who is the chair from Stellenbosch University, and Richard Long, who is a MIC1 finalist from Thales Alenia. Then we have Maximilian Bertet from the University of Tokyo. We have Munetaka Ueno from JAXA, and Shinichi Nakasuka from the University of Tokyo. And Chair, please.
Yes, good afternoon, everyone, and good luck to the finalists who will do the presentation. I'm also here only for 10 minutes, so I have to be quick through my slides. So how do I advance the slides? Okay, next slide. The contents is, I will just list the requirements, 3 requirements for Mission Idea 8. Contest 8, then a background of previous Mission Idea contests, the previous MIC winners, and the timeline and process through this competition. Look at the evaluation criteria that the reviewers will use to judge your presentations, and then a summary of the submissions, and finally the awards that will be given. Next slide. Oh, yeah. How do I go back? The requirements for this mission idea contest is to have a mission that use multiple satellites made from 6U maximum size to smaller CubeSats. The mission must have at least 2 satellites in it, and it must demonstrate clear benefits of having multiple satellites. So if you can do the mission with just 1 satellite, then it's not good enough. It must use multiple satellites in orbit simultaneously. It can be a constellation mission where you have no inter-satellite link between the satellites to coordinate, or it can be a formation flying mission with an inter-satellite link. Background, the first mission idea contest was launched in 2010, and it was set up to encourage innovative exploitation of micro and nanosatellites to provide useful capabilities and services. And it was a platform for anyone interested in space, aerospace engineers, students at universities and college students, consultants, to present their creative ideas and to gain international attention. There's a photograph of Mission Idea 3 that was held in 2014 in Kitakishu, and then Mission Idea 4 that was in Varna in Bulgaria. 7 Mission Idea contests have already been completed, and also 4 pre-MIC workshops were organized between 2011 and 2022 over a 12-year period, and the results were many utilizations of micro and nanosatellites provided in a large number of submitted proposals, and from these a couple of finalists was selected every time to present their proposals. 4 books were published as part of the IAA book series on MIC 1 to 3 as well as MIC 4. And in the MIC 4 book was also the deorbit device competition, also organized by UNISEC, and the proceedings of MIC 5 and 6 and the debris mitigation competition 2 was also presented in a book, in book form. This is a list of all the winners for the mission ideas. I'm not going to read through all the winner proposed ideas. You can do it yourself. MIC 1 was a constellation of small satellites, so we've gone the full circle. Today is also about a constellation of small satellites. MIC 2 specifically focused on satellite design, and that was won by a USA student team. The first MIC was won by a professional team from Japan. MIC 2 also had another part, a business model part, and that was won by a student team from South Africa. MIC 3, the winners from a joint professional team from Germany, Italy, and Slovenia. And MIC 4, Australian team of students. MIC 5, also a joint team of students from Taiwan, United States, and India. MIC 6 was about experiments on the International Space Station. There was 2 competitions there. The one was on the ice cube on the ISS, ice cube provider. Costa Rica student team won that one. And MIC 6, the ISS ICEEP provider was a professional team from the Philippines. And MIC 7 was a deep space mission, and that was won by a student team from Turkey. The process and timeline this time, end of June was the deadline for the abstract submissions. From those abstracts, the reviewers selected 10 finalists, and they were notified beginning of August, and they had to submit their final papers beginning of October. And from those final papers is what will be presented today in Tokyo at the 9th UNISEC-Global meeting. So there will be 6 presentations in person, and there will be 4 presentations that will be handled virtually. Evaluation criteria is basically 4 aspects that we as reviewers looked at. The originality of the presentation, 25 marks out of 100. Impact of this presentation, also 25 out of 100. And then the engineering aspects were actually 2 aspects that we looked at: technical description and solution, 20, and operational aspects, 15 marks. And then finally, the feasibility of the mission. Is it a realistic mission from a cost point of view, from a schedule point of view, the risks and the opportunities, 15 marks. We received 23 abstracts from 16 countries, so you could see it's really an international competition. And from those, 10 finalists and 2 semi-finalists were selected from 10 different countries. The constellations or formations that were selected obtained satellites in size from 1.5 U CubeSats to 6 U. The upper limit was 6 U. And the constellations were from 2 to 220 satellites. So very small constellation or formation of only 2 up to 220 satellites. The payloads were varied. Many of the missions flew hyperspectral images, multispectral images, global navigation systems, LiDARs, synthetic aperture radar, dosimeters, mass spectrometers, phase array antennas, etc. And the missions were mostly in low Earth orbit. Then there were 2 missions to the moon, Earth moon, and there was also 1 mission to Europa, the moon of Jupiter. Finally, we will select awards to what will be presented this afternoon. There's an IAA award for the best out-of-box idea, a student prize for student team. That's a monetary prize, so very good prize. And then there's a second place, and finally the first place will be handed out this afternoon, later this afternoon. Good luck to all the presenters, and that's my final word.
Thank you, Professor Stein. Now, we are very quickly start with the first team from Italy. The project title is MOTS, Moon Observation Through Hyperspectral Satellites. So here we have Michela, Alessia, and Carolina.
Can I start?
Please.
はじめまして、私たちはカロリナとミケラとアレシアとです。ロマニ大学の学生です。
Okay, now we speak in English, so we can start the presentation talking about what are transient lunar phenomena. These are short-lived changes in light, color, or appearance on the surface of the moon. And this phenomenon can range from foggy patches to permanent changes in the lunar landscape. We want to study this kind of phenomena for the future lunar missions in order to choose an appropriate moon landing site and also possible position for future lunar settlement. Moreover, to understand the color-changing effect due to this phenomena, it is important to study the correlation between the outgassing of different gases present in the moon with the moonquakes. The MOTS mission has 3 main mission objectives. The first one is the detection of color changes on the surface of the moon that will be studied in different optical wavelengths in order to locate the main affected sites, and also, if it's possible, to correlate the outgassing of argon, radon, and polonium with this kind of phenomena. The second one is to investigate the argon outgassing because this phenomena is an indicator of seismic activity on the lunar surface, so it's important to understand where this phenomena can happen for the future lunar settlement. Lastly, we want to compare the TLP observation conducted from Earth and the one conducted from the satellite in order to understand which is the effect of the Earth atmosphere on the observation of this phenomena. The mission operations are divided mainly into phases. The first one is the acquisition phase that lasts for 2 minutes and 30 seconds, and we have a total of 4 acquisition for orbit, 2 on the dark side and 2 on the visible part. After this phase, we have an onboard processing of the data, and then the download phase, which lasts 1 hour and 30 minutes for each orbit, in which all the data set will be downloaded. We set 3 different performance parameters for this mission. The first one is that the primary payload, that is an hyperspectral camera, shall have a faster resolution that is below 20 meters. This because this phenomena can have an extension between a few kilometers and 100 kilometers. The second one is to have a spectral characterization of the TLPs in the blue and the red spectral region. And the last one is that the GNSS receivers chosen as like a secondary payload acquire the L1 GPS and the E1 Galileo GPS band from the Earth GNSS constellation.
The primary payload is an hyperspectral camera, and it allows to achieve the mission objectives. The payload subsystem chooses Hyperscape 100 from Chimera Sense, and according to the mission requirement and the TLP physical dimension, the GSD at 750 kilometers of altitude is 7 meters. And this payload has a push broom imager, so the scanning methods allows to obtain the hypercube, which is a three-dimensional data. And in this way, it is possible to obtain optical images as camera sensor does, and the spectral signatures for each wavelength as a spectrometer. And the data volume is very large, and it is necessary to have on board an additional memory for its storage. The secondary payload is a GNSS receiver that will be used in support for the future LNS mission and the future human mission on lunar surface. And the main objective is to acquire the signal from the GPS and the Galileo transmitters around the Earth because the transmitted power is not directed only towards the Earth, but also toward the deep space. So in this way, it is necessary to use this constellation as a relay to support the future human mission on lunar surface. And the selected receiver is the SGR LIGO that will operate at the GPS L1 band and Galileo E1 band together with a patch antenna. In this slide is presented the internal satellite structures. On the right, it is possible to see the S-band and the X-band transceiver with the hyperspectral camera, while on the left, there are the battery pack and the power distribution unit, together with an onboard computer, reaction wheel, and the propulsion unit. And the external structures is provided by the solar panels and the antenna for communication. The OBDH uses Proton 400 KTM as a computer in order to manage the big data volume, and it is able to endure an amount of total uniting dose up to 100 kilorads with a storage capability of 256 gigabyte. For the DCS, the determination subsystem has one IMU and finds a sensor and a search tracker, while for the control subsystem, there are 4 reaction wheels in a pyramid configuration. And for the propulsion unit, we have a central thruster with 4 cold gas thrusters. About the APS, we have a battery. We have some batteries with 86 watt per hour capacity and a nano power distribution unit. And about the solar panels, they are deployable with 45 watt per wing. And the power margin computed per orbit is about 10 watt per hour.
The satellites will be equipped with both X and S-band with 3 main ground stations. The first one located in Goldstone, California, the other one in Malindi, Kenya, and the third one in Rome that is in progress. So the X-band antenna will be prioritized and used for direct-to-earth communication with a gain of 10 dBi and a data rate from 2 kilobytes per second to 200 megabytes per second. second. The passage, so the contact time will last for 1 hour and 30 minutes per orbit, and considering the data rate, the data transmitted will be 135 gigahertz. So in the table you can see the link budget with a positive link margin of 3.6 dB in downlink and 32.9 dB in uplink. The S-band will be used only in case of emergency with the Lunar Gateway and Lunar Pathfinder that will be launched in 2024. In this case, the gain is from 6 to 11 dBi and the data rate is the same as the X-band. The link margin is also positive and has a value of 19.6 dB in downlink and 41.2 in uplink. So in the table you can see the orbital parameters of the first satellites on the two different orbital planes that are spaced of 180 degrees in right ascension of ascending node. So the second and the third satellite along the two different orbits are spaced of 60 and 120 degrees into anomaly for two main reasons. The first one is to not have overlapping of the SWOTs on ground, and the second one is to obtain simultaneous observations. So the resultant daily coverage is 2.69% for all the constellation, resulting to a complete lunar surface coverage in 37 days. The Earth-to-Moon transfer is considered with these three launchers that you can see in the slide.
So now we talk about the implementation plan of this mission. The MOTS team is composed of 22 students studying for master and bachelor degrees at the Sapienza University of Rome in aerospace engineering. On the left side of the slide, you can see the implementation plan for one satellite, so the first one of the constellation. And for the first one, we will have also both the engineering model and the flight model. The first one used for qualify and test the satellite. You can see that in almost 2 years, we want to develop and launch the first satellite. On the right side of the slide, you can see the cost budget. Considering that in the IVU and testing phases, students and university facility are involved, the total cost of the mission is 7 million euros. Due to this high cost, possible governmental endorsement should be considered. So in this case, we should add also a 45% to the total cost, arriving at a total cost of 11 million euro of the mission. Here is presented the risk analysis. This is a high-risk mission due to the fact that we want to go to the moon and also due to the difficulty in the development and high cost of the mission. You can see that the higher risks are related to the project management, in particular to the development complexity and to the insufficient funding for the mission. Together with this are reported also the risks for the other subsystems. In conclusion, MOTS is a 6/6 CubeSat constellation. The primary payload is an hyperspectral camera, while the secondary payload is a GNSS receiver. We will cover the lunar surface within 37 days, and this mission wants to understand this lunar phenomenon for the future lunar exploration. Thank you so much.
Thank you very much. Okay, please, dear members of the jury.
The sun reflective angle, you want to measure with hyperspectral camera and see color changes to detect these gases. But your sun reflective angle will vary depending on where you image on the moon and where you are in your orbit. How did you take that into account?
Okay, it is a good question. And we studied the TLP phenomena, and we found out that they are linked to the color changes in terms of emission of radon and other gases that are on the moon. So it's not strictly linked only to the sun angle with respect to the moon, but also with this emission in the spectral range of the wavelength for these gases. So our objective is to study more the gas emissions in the spectral region of red and blue. respect to the acquiring the data from images. In this sense, the color changes in a spectral emission.
Yeah, but you need the sun to see the colors. So when you fly an eclipse side of the moon, your hyperspectral camera will see nothing because it's black.
No, it's true. It's true. In fact, for this reason, we decided to combine this characteristic of the sensor that it needs the solar condition, the illumination condition, together with an optimal, we can say, better configuration of the orbit in order to acquire the data in the same moment, in order to compare what it changes between a moment to another.
Okay, so thank you very much. And you are saying that in 37 days, whole the surface of the moon will be covered, and this 37 days is enough for detecting this kind of the phenomena.
Yes, because the aim of our mission is like to cover the most surface possible. So 37 days was the like better results that we obtained. So about monthly coverage is perfect because these phenomena like leave on the ground some traces. So every month you have images that you can study and say, okay, last month this like black part wasn't there. Maybe it could be a TLP. So yes, I think.
Okay,
Good.
thank you very much. One more question. So you try to get a GPS signal from the Earth orbiting GPS. So in that case, you need a very big antenna which has a high gain. So that kind of the big antenna can be accommodated to the 6U CubeSat?
Okay, in general, the GNSS receiver has hemispherical antenna, and based on what we found on literature, we found out that in some cases the GNSS signals that came back, that came toward the deep space, has quite good power, and it is possible to see this power also with an hemispherical antenna, even if it doesn't have a high gain. So we can use also the hemispherical antenna and the antenna that has a low gain. For this reason, we think that is possible.
I think yes, that's a very important point. Please, I can say check it more.
Okay. Thank you very much.
There's still time. Your propulsion system, can it generate a torque around all three axes of the satellite?
Okay.
Or is it just a single nozzle?
No, because the payload needs to have another pointing. The stabilization has to be 3 axes, and for this reason we used all the reaction wheels, the reaction wheels in a pyramid configuration, and in order to control the systems in a better way, and so we need 3-axis stabilization.
Yes, you have the reaction wheels to do that, but when you want to dump momentum from the wheels, you need to be able to generate a torque around X, Y, and Z axis with the propulsion system.
We consider that the magnetic field around the moon is not present. So we need to use, instead of the magnetotorquers, we used the propulsion system composed by a central thruster and a four-coil gasser to desaturate the wheels that are used for the control system.
And it can generate a torque around all 3 axes. It's not just a single nozzle propulsion system. It has multiple nozzles.
There are 5 total nozzles that can be moved and have different direction of ejection. So yeah, we can generate the torque in all three axes and desaturate all the three reaction wheels that are working for stabilize all the three axes.
Okay, thank you for your nice presentation. So your secondary objective is to support navigation and positioning on the moon. So to gain support for this mission, one option maybe is to partner with a lunar rover mission like iSpace. Is that something that you may consider to test the LNSS mission and potentially to get funding and support?
Yeah, this is we also consider the secondary payload also to prolongate the life of this mission. In order that we have, yes, a lot of data acquisition, but as you can see, the acquisition phase is less for a short time during one orbit. So we decided to have high performance of this mission to add the secondary payload. Yes, we thinking about possible funding with this kind of future mission, with possible also agencies that work in space. So yeah, it's a possible solution for our funding mission. Thank you so much.
Thank you. So end-of-life operations are going to be critical to lunar sustainability in the future. I wonder if you could just describe the considerations you give to end-of-life disposal so as not to create a debris hazard or take up valuable orbital real estate.
Our consideration were that probably as now from Earth, there will be a graveyard orbit for future lunar satellites. The second one is that we have thrusters, so we can put the satellite in orbit around the sun. So these are two solutions that we considered. Moreover, we have like different contact with the AIDC, in particular in the mitigation debris committee. So with our supervisors, we think that this could be two possible solutions for our disposal of our mission.
Okay, now we have the second team from Politehnica Bucharest, from Romania. The mission name is Lunaris. We have David Emanuel, Remus Mihail, Robert Andrei, and Andrea Elena, and Maria Alexandra. Team of 5. Okay, 4 here. 5, okay.
Konnichiwa, we are Lunaris. Please have a look at our video presentation, and we're waiting questions afterwards.
And today we will present our nano-satellite constellation concept, Lunaris Unveiling the Unknown. Now, to give a bit of context for this mission concept, by studying upcoming space missions, it is immediately clear that a large number of moon-related missions are planned or in development, as the interest in lunar mining has increased significantly in recent years. It would therefore be logical to assume that there is a pressing need to enhance our understanding of lunar topography in order to facilitate the navigation of its surface. For this purpose, Lunaris Unveiling the Unknown aims to 3D map the lunar surface and overlay it with a map of its chemical composition in order to enhance navigational capabilities and facilitate the identification of future potential landing and habitation sites, as well as locations of interest for space mining. For mission objectives, the primary objectives are to create a three-dimensional map of at least 95% of the lunar surface, as well as to analyze and determine its chemical composition. For secondary objectives, the mission aims to establish a system that provides a dynamic, up-to-date map of the moon that will facilitate effective monitoring of changes, and to provide an opportunity for space enthusiasts and radio amateurs to develop their skills by receiving images and data sent from the satellites. The concept of operations. The mission will consist of a constellation of 2 6U CubeSats on a frozen circular orbit around the moon, located at an altitude of 100 kilometers from the lunar surface. The satellites will be placed 180 degrees apart from each other and will use their LiDAR and hyperspectral camera to scan the moon's topography, as well as the terrain's composition. The constellation will use the future Moonlight constellation for positioning, which is essential for the LiDAR, and the future lunar gateway as a relay between the CubeSats and the Earth. The mission will be launched alongside Moonlight's modules on a preliminary selenocentric orbit. From there, the satellites enter initial mode, in which all initial checks and configurations are performed, as well as calibrations of the equipment and payload. After detumbling, the satellites will use propulsion in order to reach the desired orbit. Nominal and transmission modes are very similar, both involving payload operation, data collection, and compression by the OBC, the difference being that during transmission, the data gathered during the last cycle is passed to gateway to be redirected towards the Earth. Once the mission is complete, the satellites will enter the end-of-life mode, where they will use the remaining fuel in order to crash into a designated spot on the lunar surface, while also powering off all systems. The satellites will also enter safe mode anytime an abnormality or error occurs, which they cannot solve by themselves, or the battery state of charge falls below 40%. For key performance parameters, the camera resolution needs to have a GSD of 30 or even lower at 100 kilometers altitude, and the HyperScout M from Cosine fits this criteria with a GSD of 39 at 350 kilometers altitude. A full scanning cycle should take place in approximately 1 month to produce a precise scan of the lunar surface, and using the chosen frozen orbit, it was calculated that the mission would complete a full scan in approximately 27 days. The CubeSats need to always be at 100 kilometers altitude in order to maintain a constant resolution for the images. This can be achieved through the use of a propulsion to correct the change of 2 degrees in inclination, which occurs once every moon rotation cycle.
Up next, I'll be talking about our mission's space segment. As you already know, the two CubeSats in questions are equipped with a LiDAR and respectively a hyperspectral camera. The LiDAR boasts a size of 2U, a considerable amount of the available space. However, it definitely makes up for the downside, as it is able to complete a scan of its given range in less than a second. This technology holds a lot of promise for the future, as it is currently being developed by many companies, such as Fiberlink. The hyperspectral camera only takes up 1U, allowing more space for other equipment. It is a reliable and tested technology. The model we chose for our CubeSat being the HyperScout M from Cosine. Here you can see a CAD representation of the two CubeSats, and here you can observe an exploded view of the LiDAR CubeSat, presenting all of its main components. After calculations, we determined that the maximum mission time would be of 201 days, 7.5 moon rotations, consuming 2.7, respectively 2.09 kilograms of fuel for each satellite. Moving along, I'll be going over a brief overview of the power budget. A rough approximation of the power consumption of each operational mode was calculated. For the majority of them, in the worst case in which the satellite is in eclipse, approximately 46.8 minutes, the battery state of charge reaches about 71%. By far, the largest power consumption is during orbit insertion and end-of-life modes, when the engines are running. For this reason, it has been estimated that the two 6U and one 3U solar arrays should be enough to account for this loss. If further calculations deem the budget for these two modes negative, deployable solar panels have also been considered.
Now, let's talk about communications. Communications will function in the S-band for Moonlight and K-band for Gateway, as it has a bigger range that can reach the lunar station when it is at the maximum distance from the satellite. To this link, payload data and housekeeping reports will be sent to Gateway, acting as a relay that will redirect them to ground stations situated on Earth. From there, the data will be sent to the mission's ground facilities. For communication with the Moonlight constellation, an S-band system was considered, and commands will also be sent to the satellites through the systems that will be developed with Gateway and Moonlight. A detail that was considered is that the satellites will have a special K-band frequency reserved for amateurs on Earth that, when possible, will be able to receive signals transmitted from the satellites, or even images of the Moon. This will not have any impact on the mission, as this would only occur when the CubeSats are not engaged in tasks involving the primary mission, like transmitting to Gateway. Also, the leader satellite will send versions of the 3D map so that the hyperspectral camera can perform the onboard processing. Data budget. For housekeeping data, a data budget was computed as described on this slide. The grand total of housekeeping data for one orbit is 570 megabytes, but not all of it is transmitted to the gateway. A daily report that will contain a brief history of the system to ensure that it is working properly will be sent, and if any of the satellites enter safe mode, this information can be set soon. This report will have a low dimension below 100 megabytes, and for each of the satellites, a size of 64 gigabytes was chosen, in order to ensure that, in the worst-case scenario where a transmission cannot occur for several days, the critical data can be stored until the next possibility to transmit.
About data storage. To store the collected data, non-flash memory from 3D Plus will be used. It has a higher storage capacity, the erase and write operations are quick, it is radiation resistant, and that reduces the possibility of bitlets. The hyperspectral camera has 192 GB storage capability, which would be sufficient to store data for at least 2 or 3 orbits. 2 storage modules of 128 GB will be used, one for backup and one for the lunar map. Regarding the LiDAR CubeSat, the equipment is still in development, so an exact amount of data could not be computed, but 2 storage modules of 128 GB were considered sufficient. Data processing. The hyperspectral camera has onboard processing capability, which is possible if a map of the moon surface is stored on board. For LiDAR CubeSat, to avoid a large data flow, an onboard processing unit is considered to perform lossless compression. This processing unit includes a microprocessor, pre-processing steps such as data calibration, noise removal, and filtering, and lossless compression techniques based on improved LZW and Hubman algorithm.
Next up, orbit and constellation description. Why a constellation? For two main reasons. There is not enough space on a 6U CubeSat for the necessary payload, and using two separate satellites create more redundancy in the design of our mission, meaning that even if one satellite faces an unfortunate fate, half of the requirements of the missions will still be satisfied. The orbit chosen was circular low lunar orbit with an altitude of 100 kilometers, as it was limited by the range of our payload. Due to it being at such a low altitude, the lunar mass cons would affect the orbital stability of the satellites, hence a lunar frozen orbit would be optimal for our mission. From the possible choices, an 86-degree inclination frozen polar orbit was chosen due to it providing the most coverage of the lunar surface. The satellites share the same orbital plane with an orbital period of approximately 2 hours. The coverage of the satellites would be 99.84% for the LiDAR CubeSat and 99.92% for the hyperspectral camera CubeSat per orbit cycle. In conclusion, only a smart portion of the poles isn't covered by the mission. Regarding the implementation plan, potential sponsors would be Romanian branches of companies such as GMV, Thales, and Demos, Romanian companies like Comoti, Incas, and Rice, and NGOs, namely Rospin. For testing facilities, we will need shock and vibration testing facilities, access to a vacuum chamber and a clean room, as well as software tools. Regarding the costs, a complete price estimate was conducted for the mission and its development, which resulted in approximately 60 million euros. Comparing it to prices of similar lunar CubeSat missions, like Lunar IceCube and Capstone, it was concluded that the price is regular for a deep space graded mission, and the valuable information that the mission provides justifies the cost. On the risk table, we mainly listed external factors that are independent of the mission's development, such as launch, lunar gateway and moonlight missions, and funding, as well as ways of preventing them. Of course, risks of malfunction exist in all of our components, and we took proper backup measures where possible. On the Gantt table, we summarized our mission's timeline, from designing to manufacturing and the utilization of the satellites, finishing with the disposal procedure. The disposal procedure will occur in two cases: if the satellites encounter critical damage, or if 201 days pass and there is not enough fuel on board. For the end of life, we chose to crash our satellites into the moon in a potential satellite graveyard. This graveyard would be chosen by analyzing the data gathered by the mission and finding an area with little prospect for future lunar missions. That was all from us. Thanks for the attention, and we are awaiting further questions.
Thank you, team. Please.
Thank you for the presentation. I just have two questions about your ADCS system. In your paper, you said you're going to desaturate the wheels using magnetorquers. That will not work around the moon. The moon doesn't have a magnetic field that's strong enough for magnetorquers to do the job. The other thing is your ADCS system is much too small. If you have wheels, it cannot just be 140 grams for the total weight of the ADCS system. I'm not sure what you plan to use or to buy for ADCS, or will you develop it yourselves?
When we studied potential ADCS systems, we looked at commercial off-the-shelf ADCS systems, and that is the one from the table we used for the approximations. About the magnetotorquers, yes, we haven't taken that into consideration, so I think further analysis on the ADCS system should be made in order to correct this.
Okay, so thank you. And the data, mission data will be downlinked to the ground by using the S-band or using the K-band, and it will go to the moon gateway, which is correct?
The payload data will be transmitted to the gateway, and gateway will use the ground stations on Earth that will be assigned when the mission will be launched. And from there, the data will be sent to the facilities that we design and award the customers.
So if the data is go via gateway. So you calculated how frequently the satellite can access to the gateway.
Yeah.
And how long?
Yeah.
Okay. And so the generated data, all the data can be downlinked to the ground via gateway, right?
Yeah.
In your calculation. Okay, good.
Yeah.
And so you are saying that this is a two satellite, and one is a LiDAR, and one is a hyperspectral data. But it seems that it's not like a constellation. So just like a two satellite. So is there some synergetic effect using these two different kind of the sensors in order to obtain a certain outcomes?
Could you repeat the last part of the question, please?
Yes, you have the hyperspectral, satellite, and the one is LiDAR satellite. It seems that these are just one satellite and one satellite. It does not seem like a constellation. Okay, so in order to be a constellation, maybe these two different sensors will generate a certain synergetic effect. So do you have some kind of the idea like that?
About the synergetic effect?
Yeah.
Yes. We want a complete map of the moon. That means topography and chemical analysis. In order to facilitate the future lunar missions that are about to come, we need to know the potential locations for bases, landing sites, and mining sites. And that is why the synergy between the topography and the chemical composition of the moon is required.
Okay, I understand. Thank you.
Thank you for a nice presentation. I have a question about the hyperspectral camera. So to measure the chemical composition of the surface, which spectral bands do you think will be important, and what types of indices do you plan to measure?
I don't think we've gone into analysis that far, but it's something we are considering for the future, yes.
Okay, thank you.
I've asked a question to the previous team as well. If you use a hyperspectral camera and you have a certain coverage that you set 97% or 98%, that you take the eclipse part of the moon into account where the hyperspectral camera cannot give you any measurements?
We did not take the eclipse into account. We didn't consider that.
That is true, but we have time in our mission lifetime to orbit the moon multiple times, so that should account for the loss when the satellites are in eclipse.
Yeah, I think the figure that you quoted in your slides was in 27 days per month, you covered 97% of the moon with the hyperspectral camera. So you should take into account when you do that calculation, the part where you're in eclipse and you cannot use the hyperspectral camera.
Yes.
Okay, I have another question. So in your concept of operations, you seem to perform calibration of the imager and sensors first, and then you detumble the satellite. So is it necessary to detumble first and then calibrate, or is it okay to calibrate first and then detumble?
No, I guess it would be better to detumble first and then calibrate in order to have better images and better accuracy of what the instruments can do, so that we can make sure that they are working correctly.
Okay, yeah. Thank you.
Just one, again, a question about debris mitigation and end of life. So you propose to crash the spacecraft into the moon. So it's an interesting idea to specify a particular graveyard site. What can you do in the event of a failure of a system which is going to control that, and how accurately can you assure reaching that particular site?
We've taken into account error margins that could lead to this. We've added extra fuel to make sure that we can crash on the moon. If it's not possible to crash into the designed location that we want to make a moon graveyard, that's okay. But at least we'll find that spot where we would want to crash, and we would find best on the moon to erase basically the space debris problem. Because if we were going to create another graveyard orbit around the moon, that would come with a lot of other problems in the future.
Any further questions?
A very brief one. So your thruster seems to be positioned away from the center of the satellite, so it's towards one side of the 6U. So do you expect this will produce some kind of torque, and how do you plan to counteract this when you activate the thruster?
Initially, it was planned to be done by the AEDCS system, but as stated before, that needs to be taken into further consideration. So we will go over it and redesign that part.
Okay, if there is, we can take one more question or we can conclude. Okay, then thank you very much, team. So our third team is from South Africa, Stellenbosch University, LEO Backup Earth Navigation System, Tian Siliers.
Good day, everyone. Today I'll be presenting my team's submission to the 8th UNISEC-Satellite Mission Idea Contest. So our submission is titled LEO Beans, or the Backup Earth Navigation System, a phased array Ka-band CubeSat constellation pointing navigation and timing, or positioning navigation timing solution with the goal of increased reliability. So first of all, I'd like to introduce my team. So my team consists of Dirk Slabber, Lauren Cook, Jurgen van der Merwe, Saad Badat, Michaela Isebek, Philip Lotriet, Rowan Twilly, and of course myself, Tian Slier. I would also just like to mention we're all students at the Electronic Systems Laboratory at Stellenbosch University in South Africa. So to put this proposal into a bit of context, GNSS global navigation satellite systems are not perfect. So I am, by chance, involved with some rescue work in my country, and we're often faced with situations like you see there on the screen, where we're working in very dense vegetation surrounded by steep cliffs, and as a result, the accuracy of GNSS solutions is very low, as you can see on the right here. This is because not only is there a very low amount of satellites visible, increasing the difficulty of triangulation, but vegetation and cliffs also affect signal strength adversely. So this is only one of the many scenarios in which GNSS solutions fail. I don't know how many of you might have noticed in the streets of Tokyo, sometimes the buildings also affect GNSS accuracy. So while they normally deliver excellent accuracy, there's some improvements that can be made in reliability. So for this reason, we have the following mission objectives and performance parameters for this proposal. We propose to transmit a novel positioning, navigation, and timing signal from a constellation of CubeSats. We propose to do this in a frequency band which is less susceptible to ionospheric scintillation and multipath error, and to increase the number of satellites visible at any point while still ensuring a sufficiently high signal-to-noise ratio to allow the signals to be received by stations on the ground. Finally, we would also like our satellites to be a lot cheaper than traditional GNSS solutions, so that the system can be more easily scaled to larger amounts of satellites. So the concept of operations for our proposal is as follows. We will have a constellation of 6 U-CubeSats in low Earth orbit. These satellites will receive data from existing GNSS satellites in the L-band, and this will be used to calculate the satellite's position, as well as to calculate the clock drift on each satellite, so that we don't need high accuracy atomic clocks on all our satellites. So we will then transmit a custom Ka-band signal from our constellation satellites down to Earth, and this will be done using a phased array antenna to reduce power consumption needed. The following is an overview of our satellite design. It will consist of a Ka-band phased array antenna, a VHF UHF transceiver for telemetry tracking and control, an L-band antenna to receive the signal from traditional GNSS satellites, as well as standard CubeSat components, including an electrical power system, onboard computer, attitude determination and control system, and a propulsion unit. So a novel component of this proposal is the use of a phased array antenna to transmit PNT data to users. We've proposed this to be a custom part developed for our constellation. However, there are many existing phased array antennas offered for CubeSats. So it is proposed to have an electronically steered beam swept to cover our service area for each satellite. And our calculations achieve this by using a 24 by 24 grid of elements with a 30 decibel Chebyshev tapering to minimize side lobes. This is then combined with a time division multiple access scheme to ensure that our satellites can access the required area with low power usage by using a higher directivity antenna and selectively allocating availability to areas where the system is registered to be used. Other components in our design would include an ISI space EPS, an ISI space onboard computer, cube space ADCS, a glide space GNSS receiver and UHF/VHF transceiver, an impulsion nano field emission electric propulsion thruster, ISI space deployable solar panels, and an Aurora propulsion systems plasma brake. For more information on our link and power budgets, please see our full paper. So quite a lot of work has gone into designing an optimal orbit for this constellation. We've chosen an orbit altitude of 1,000 kilometers as a trade-off between radiation levels and delta V requirements growing at higher altitudes, and the available service area decreasing at lower altitudes. Our final constellation consists of a Walker Delta layout of 18 planes of 7 satellites per plane for a total of 126 satellites. It should also be noted that each of these planes include 1 spare satellite. Our planes would be at an inclination of 49.1 degrees, ensuring at least 5 satellites visible for all locations at all times between the operational latitudes of 60 degrees north and south. This layout results in significantly more satellites visible on average than this number, growing up to 13 satellites visible at some times. And having more satellites available leads to a higher accuracy when least squares solving of the positioning equations are used. Shown on the right here is all of the satellites visible from Tokyo at some point in time. We've also done a Monte Carlo simulation to estimate the geometric dilution of precision resulting from the layout of our constellation. And this number was found to be less than 4 for all locations in our service area, as well as less than 2 for the majority of the service area. And you can see this on this graph on the screen. Yes, so these numbers for geometric dilution of precision are quite low, lower than traditional GNSS systems, and this is because we have such a high amount of satellites that it's possible to triangulate positions more effectively. So our proposed in-orbit operations consist of the following. A launch would place the satellites in a 300 by 1,000 kilometer orbit, such that they can passively deorbit if they cannot be actively controlled. After reaching this orbit, the satellites would use their impulsion nano propulsion system to raise their perigee and phase their right ascension of ascending node over roughly a year. Calculations have shown that with a single launch, yes, they will be able to reach all planes within a year, phasing at a perigee altitude of 400 kilometers. The same propulsion system will then be used for collision avoidance over the lifespan of the satellite and would drop the perigee back down at the end of life for deorbiting. A total delta V number of 570 meters per second have been calculated for a 10 kilogram satellite, which is divided in 370 meters per second for orbit raise and lower and 200 meters per second for collision avoidance. The implementation plan proposed for our satellites is as follows. We would execute the plan in 3 phases. The first phase proposed would be to develop a single satellite in a university context as a proof of concept. In the second phase, a small number of satellites would be built and launched to confirm functionality in a constellation environment. Finally, after functionality is confirmed, the full constellation can be developed, deployed, and maintained in the third phase. The following risks have been found with our mission proposal. Firstly, regulatory hurdles, especially considering the planned active deorbiting and constellation size, can be a problem. Funding difficulty should also be considered, as this proposal can become quite costly, as estimated in our budget. However, there are significant economic opportunities when increased reliability can be offered for GNSS. Technical problems relating to the extreme precision required can also be a problem. However, so for example, if the clock drift cannot be accurately estimated based on legacy GNSS signals, the constellation would not be feasible. In-orbit failure of satellites and other operational problems can also be a risk later on in the development cycle. So in summary, we've proposed a novel solution for enhancing GNSS reliability. This solution would use Ka band transmissions, which should be more resistant to ionospheric scintillation and obstructions. Phased array antennas would also allow for broad coverage angles while still consuming little enough power to be able to fit the solution on CubeSat size. This would significantly decrease the deployment costs compared to legacy GNSS satellites, And the solution would thus offer a forward-looking strategy to address pointing, navigation, and timing demands of modern technology, urbanization, and rapid humanitarian response. Thank you, Nkosi, danki, arigato gozaimasu, dekodasai.
Okay, thank you for, well, quick presentation to say, please.
I have a question, question about your processing need for your payload onboard computer. You want to do all the antenna phasing of the 24 by 24 elements, the GNSS processing, the pseudocode generation, all of that in one microblaze soft-core computer. And it only consumes, according to your paper, 3 watts. Is that feasible, that you do the analysis on that, or was it just a guesstimate?
I personally didn't do that calculation. However, the person responsible for that is currently working on a FPGA system for CubeSats. So I assume there has been at least some calculations into what type of FPGA would be able to be used for that. Thank you.
Okay. So thank you very much. So what is the current estimate of the accuracy, positioning accuracy on the ground?
So as a rough number, with a geometric dilution of precision of 4, that means that the accuracy achieved would be 4 times the error in ranging from each satellite. So if you can get, for example, an estimate within 10 meters of your satellite, that would mean 40-meter accuracy. However, due to the lower ionospheric scintillation, you should be able to get accuracy much lower than that. Thank you.
So would you give us some number, a concrete number? Maybe several meter or several tens of the meter?
We would estimate it to be several meters.
Several meters.
Thank you.
So very similar to the GPS or Galileo.
Yes, correct. Okay. But hopefully, when scaling with larger number of satellites, allowing better accuracy when only a restricted field of view is visible or in foliage cover.
Okay. And another question is that maybe I think the highest risk will be to frequency license. Maybe so, you know, that K-band is very much congested and it's very difficult to obtain the frequency license. Do you think you can get the frequency license for a K-band for such kind of the large number of satellites all over the world?
Thank you for the question. So we have not considered frequency licenses in our risk analysis. However, I would assume since we are planning to use time division multiple access instead of frequency division, or we might need a narrower frequency band, and it might be easier to use a single frequency for all our satellites. Thank you.
Okay, thank you very much. So one more question. And you said that the atomic clock will not be implemented in the satellite, right?
So we would be planning to use chip-scale atomic clocks on each satellite. However, these could be a lot smaller, and while they would have drift, we would be able to cancel out this drift by using the drift estimation from the accurate legacy GNSS satellites.
Okay, thank you very much.
Thank you.
You mentioned a risk based on for the quality of the signal, the performance based on legacy GNSS signals. Is that something you can de-risk or remove in analysis beforehand, or is it something that's fundamental to the system and you just have to live with the possibility of that happening?
So this should be something that we could de-risk. In our research, we found that there are quite significant relativistic effects to consider when working with GNSS systems, and none of us are experts in that field. However, I'm sure with enough expertise in that field, it should be able to de-risk that before moving into operational phase. Thank you.
So in the worst case where your propulsion system fails and you use the plasma brake, what's the timescale expected for deorbit?
I have not been that involved in that system, so I would not be able to tell you an answer on that. Yes, I'm not exactly sure what timescale we'd be looking at. Sorry.
So similar to Professor Nakaska's question, so Ka-band is quite congested. Do you think interference could be an issue? Not just licensing, but do you think there could be interference with Starlink or Iridium or the other constellations?
Yes, I suppose that could be an issue if frequency bands are used that are close to each other. However, with a high data rate in our transmission system, I suppose we would also be able to use error correcting codes and things to minimize the effect of that. Thank you.
Okay, so would you give us a little more explanation about how the launch will be made? So there are very many satellites and how the launch will be made.
So yes, for that we would require a custom deployment hardware. We have not done any design into that aspect yet. However, with the simple format of a 6U CubeSat, I would assume that something similar to how Starlink is deploying satellites might be feasible. Or in the worst case, even just using multiple deployers for each satellite. The satellites are so light that even with deployment hardware mass on the scale of the satellite mass, it should still be able to fit all the satellites on one launch. Thank you.
All the satellite in one launch? Yeah, because you will deploy the satellite into the 18 orbital plane, right?
Yes.
And so in that case, maybe it's very difficult to launch all of them all together. So how do you think about that?
Yes, so our deployment plan consists of right ascension of ascending node phasing. So the satellites would one by one raise their orbit, and depending on the different apogee and perigee altitude, there would be a difference in right angle of ascending node drift, which would allow the satellites to phase to the planes in roughly a year with the heights that we are looking at.
Okay, so that means you will use difference of the perturbation of the each satellite, and in that case, it will take very long time.
We did do the calculations, and with the phasing satellites in an orbit by 400 by 1,000 kilometers and the operational 1,000 by 1,000 kilometers, the calculations show roughly a year for a 360-degree drift.
A year?
A year, yes,
okay,
correct.
Okay, thank you very much.
Pleasure, thanks.
We still have time, but we can conclude.
Just the last point from me. It's a large amount of satellites, 126, and to obtain funding for this project should be a huge risk. I imagine you've already listed that as a risk.
Yes, correct. We have listed this as a risk. However, in the second phase of our proposal, we do propose to test the system using a lower amount of CubeSats. So how this would be done would be to put some CubeSats relatively close to each other in a relative similar orbital plane so that they are spread apart, yet they all pass over a certain location at some time, and it could be tested and confirmed functional before the investment is made to build 126 satellites. So that is one way which it could be de-risked. But yes, funding would be a risk. We have considered that. Thanks.
And the ground receiver still needs to be developed, and that also has a huge financial sort of upside. Eventually, they will have to sell all these special receivers.
Yes, that's correct. A custom ground receiver would have to be developed. Yes, that is also correct. That is something that would need to be done. Thanks.
I think, please.
Thank you for your talk. And you introduced us your altitude, orbital altitude was fixed from several factors. And could you tell us a little bit of detail about the factors you use for the altitude?
Okay, great. That's a great question. So when using lower altitudes than 1,000 kilometers, we are limited by the horizon for how much area of the Earth we can cover at any certain point. We're also limited by the cone our phased array antenna, how far off bore site it can actually communicate, as well as the range. So depending on the signal strength and the path length. So those are all factors that decrease the range if you drop to a lower altitude. However, if you go to a higher altitude, you run into issues with radiation in the Van Allen belts, as well as higher delta V requirements to get there and to get back down.
Further questions? Okay, thank you very much. Now we have a video presentation from India. The title is Europa Reconnaissance Formation Mission from Institute of Science and Technology in Kutankalatur.
Hello everyone, this is Europa Reconnaissance Formation Mission, a 6U CubeSat formation mission that aims to orbit Jupiter's icy moon Europa. My name is Pranil Sharma and our team consists of Aditya Raj Bhatia, Dhanush Mamlipalli and Yash Verma. We are second year aerospace engineering students at SRM Institute of Science and Technology, Kutankalatur in India. Now the question is, why Europa? Why not Mars or any other target? Well, Europa is the prime target to search for extraterrestrial life. It has water ice and most probably has a subsurface ocean underneath it. Let us talk about the mission objectives of ERFM, or Europa Reconnaissance Formation Mission. The first major objective of this mission is to map the underground topology of Europa using an ice-penetrating radar. After that, we want to determine the surface composition of Europa, which is done with the help of a mass spectrometer. And with that, we will also be measuring the magnetic field of Europa in a stable orbit. Another important aspect of this mission is to capture high-resolution images of Europa's surface. We also will be generating a high-quality 3D model of Europa's surface using a LiDAR, and we intend to combine the high-resolution images with the LiDAR to produce a great 3D detailed map of Europa. Let us talk about the launch and orbital design. This mission begins with the launch on 27 January 2027 in Cape Canaveral, Florida, in USA. We are using SpaceX Falcon 9 full-size model as a launch vehicle, which initially puts us into a stable Earth orbit of 200 kilometers. At an injection angle of about 124.5 degrees, the second stage of Falcon 9 puts the payload into a heliocentric orbit with an excess velocity of 4.336 kilometers per second. The highest point in the heliocentric orbit of the epihelion is about 320.5 million kilometers. In this one, 3.48 kilometers per second of delta V is provided by the second stage of Falcon 9, and the remaining 858 meters per second of delta V is provided by the RAG engine in the carry stage. The Falcon 9 then decouples and is set for a cruise phase. Then, on 30th March 2028, a 1,446 meters per second of delta V burn is performed in order to get an Earth flyby with a perigee altitude of 852 kilometers and an inclination of 18 degrees relative to Earth. Here you can see a small green line connecting the Earth and the satellite. That is a communication line between the deep space network and the satellite. On 8 January 2029, a small trajectory correction maneuver is done in order to get a Jupiter approach. This is done so as to get a much more precise approach around Jupiter and to attain the required perigee or perigee of altitude and the inclination. After that, we are set for a cruise phase, and until 6 February 2032, we arrive at the Jupiter sphere of influence, and a small 7.1 meters per second of burn is done in order to get a Ganymede flyby. After that, on 19th March 2032, we do a 488 meters per second burn in order to get into Jupiter orbit, followed by a small another burn for Ganymede flyby. After that, these flybys are done in order to reduce the apogee of the satellite in order to get a Europa encounter, which requires less delta V. There are few cruise periods before Europa encounter, and on June 11, 2025, a 3,219.4 meters per second of burn is done in order to get a stable orbit around Europa. The final inclination of the orbit is not yet decided. It can only be decided after a few inputs from the current researchers in the field. This formation does not require any propulsion, and therefore there is no onboard propulsion system on every satellite. Here you can see the satellites are deployed. And this is the animation for the launch, orbital design, and deployment.
Hi, my name is Dhanush, and this is carrier stage for our mission. Let's turn our attention towards RAG engine, known for Rapid Astrogative Adaptive Generator. RAG is a 1.5 kilonewton hypergolic liquid engine designed by us for Europa Reconnaissance Mission. It is fueled by monomethyl hydrogen as a fuel and dinitrotetraoxide as an oxidizer with a chamber pressure of 800 psi or 55 bars. There are 48,000 ragas in Indian classical music, but 6 main ones from which these are derived. These 6 primary ragas correspond to 6 burns of our engine. The potent rag, Bhairav, symbolizes the highest burn with delta V of 3,220 meters per second for Europa orbital injection, performed by rag engine. The delta V budget source, the burn time, burn name, fuel burn, and of course delta V for our mission.
This is our first recon sat called CamSat. It uses a narrow field camera with 39 meter resolution and 80 kilometer swath with a wide field camera of 3 meter resolution and 12 kilometer swath to capture high resolution images of Europa's surface. By combining these images, we generate high quality images that enhances the study of geological features, ancient lakes, rivers, etc. on Europa. This approach would provide detailed imaging of specific areas in broad coverage for a comprehensive understanding of the moon's surface and potential specific interests for future landings.
Let's move on to SciSat, which carries scientific instruments like HPMI and LiDAR. Our HPMI package, known for high precision magnetometer instrument, has a scalar coupled dark state magnetometer which has range of plus or minus 50,000 nanotesla and accuracy of 4 picotesla with sampling rate of 32 or 120 Hz. And our HPMI also consists of two vector magnetometer called anisotropic magnetoresistance magnetometer, which has range of plus or minus 65,000 nanotesla with accuracy of less than 8 nanotesla. Since AMR magnetometers are not zero field detection devices, we use full Wheatstone-based configurations, feedback control systems, and two AMR magnetometers kept in planar gradiometry configurations. These make AMR magnetometers zero field detection devices and can withstand the intense magnetic field of Jupiter.
My name is Yash, and I'm going to be talking about the LiDAR's role in our mission. One of our crucial tools in this mission is the LiDAR, which stands for Light Detection and Ranging, a technology that uses light to map and peer through Europa's icy crust, penetrating its surface with laser pulses. These pulses bounce back, unveiling the terrestrial topography and potentially revealing subsurface oceans, which could be crucial in a quest for extraterrestrial life. It's not just about mapping, it's about unraveling the hidden stories within the celestial body. The 3D mapping data acquired from the LiDAR of range 1000 km, when combined with the data of other sensors from CAMSAT, will help us make a replica of the terrain of Europa with huge accuracy. Since LiDAR relies on emitted laser pulses and their reflections, it is unhindered by the absence of natural light. This means that we can even get the topography of a region which does not receive sunlight. Also, Europa is tidally locked, so the satellite will be going over the same region over and over again, enabling us to get detailed data about the region under observation.
Now I'll be telling you about the mass spectrometer. We are using the low energy ion neutral mass spectrometer INNS, which is a compact instrument designed for inside measurements on Europa. It is capable of analyzing ions and neutrals such as hydrogen, helium, oxygen, etc. It was developed by NASA's Goddard Space Flight Center in a mass range of 1 to 40 AMU. Compounds such as carbon, nitrogen, oxygen, sulfur can be detected using mass spectrometer, which are essential for life growth.
This is RadarSat. The major objective of this satellite is to map the underground topology of Europa, to determine the ice shells, thermal conductivity, and confirm the presence of a global subsurface ocean. This is done by using ice penetrating radar, which for our case we have named as EIPR or Europa Ice Penetrating Radar. The EIPR consists of a frontier radio multilingual, which sends pulses of 9 MHz towards the ground, which then penetrate the ground and detect the changes in subsurface based on the differences in permissivities. To send these pulses, we are using two monopole antennas, each 8 meters in length, with a transmission power of 20 watts. Here, we have two possible alternatives. We can either use a high frequency or very high frequency. The major difference is if we use HF, the radio waves can penetrate deep into the ground with a vertical resolution of 300 meters, but VHF configuration can penetrate up to 3 kilometers with a high resolution of 30 meters. This also helps in proposing future landing sites. For example, places that have thin ice-water interface could be probable zones for landing, as water samples can be taken easily.
Now we move on to the relay system. The relay system is basically a messenger. It features a frontier radio orchestrating intricate communications with Earth, utilizing channel 24, frequencies of 7173.87 MHz for ascent and 842.858 MHz for descent, facilitate Earth and relay communications. For cosmic dialogues with reconnaissance satellites, also called as reconsats, on channel 33, frequencies of 7184.27 MHz and 8440.80 MHz are employed. Frontier radio achieves data speeds of up to 25 Mbps with potential for higher speeds using advanced modulation techniques. It gracefully receives data at rates up to 1.3 Mbps through the cosmic language of the QPSK. Empowered by a celestial transmission power of 30 watts, it plays a key role in receiving data from satellites, forwarding messages to Earth, and executing commands from Earth to the satellites. Relay's range extends to a high gain antenna, or HGA, boasting precision beyond the celestial norm. With an accuracy level of plus or minus 0.1 degree, the high gain antenna, composed of circularly polarized unit cells, ensures steadfast communication links between the relay and the Earth.
ADC is also known for accurate determination under subsystems, which has fine and coarse sun sensor, a stack tracker, and a reaction wheel kept in the tetrahedral configuration. ADCS controls CGT designed by MOG, which has specific impulse of 57 seconds and has thrust of 3.6 newtons. These all are powered by Titan 350 Watt-hour module power array with 84,000 milliamp-hour.
Mission risks. Every mission comes with risks. The major one for our mission are micrometeoroids. As we are aiming to reach Jupiter, there is a big asteroid belt between the orbit of Mars and Jupiter, which poses serious threat to the mission. A collision with a small meteorite with our payload could be fatal to the mission. So, for that, we have added a thick fairing which houses the CubeSats and protects them in the interplanetary cruise phase. Another mission risk is radiation. Jupiter has the highest radiation in whole of solar system. Radiation can affect the electronic systems of the satellite and can degrade the mission. For example, back in 1962, Telstar 1 was an early high-profile casualty. Its transistors suffered degradation that passes through the inner Van Allen radiation belt. To counter this, we have added radiation vaults inside each satellite, which hold the essential electronics. Also, most of our components are radiation hardened and can survive the 5.4 sieverts of radiation per day around Europa. In case of an engine failure, no maneuvering is possible, and the mission cannot be completed. Toward this, multiple testings of engines should be performed on the land before launch, so that we gain confidence in the engine. In case of relay failure, the reconsats can communicate the data to Earth via Europa Clipper launched by NASA. This is possible because Europa Clipper has a relay feature and our reconsats to relay uplink frequencies are compatible with Europa Clipper. I would now like to talk about the mission impacts. This mission has various impacts in various sectors, the first one being global cooperation. International collaboration in this mission not only leverages the strength of multiple nations, but also fosters a sense of shared purpose and mutual benefit in advancing our understanding of the solar system and beyond. Collaborative missions, especially those involving multiple countries, can promote international cooperation in space exploration. Shared resources and expertise can strengthen diplomatic ties and contribute to a global effort of understanding our solar system. This mission serves as a catalyst for innovation in various sectors by showcasing the importance of ambitious goals and pushing the boundaries of what is technologically possible. This not only opens research opportunities in aerospace, but also other fields like radio, structures, etc. This project requires collaborative efforts from various organizations and experts to design, fabricate, and test the electronics, structures, telemetry, propulsion, instruments, final assembly, and testing. All of us here started with a shared dream of space and possibility. This mission demonstrates a shared commitment to advancing scientific knowledge and exploration. This threat to Europa has the potential to go beyond scientific discoveries, influencing society by inspiring, educating, and prompting reflections on a place in the universe. It can foster collaboration, drive technological innovation, and contribute to a broader cultural and philosophical dialogue about exploration and the search for life beyond Earth. As technology advances and missions are planned and executed, these impacts will continue to evolve. Thank you for giving your time. We will take your questions in the Q&A session.
Okay, thank you, team. So it was fast speaking, 10 minutes. Please, the jury.
Yes, sorry, I cannot speak that fast. The LiDAR range is maximum 1,000 kilometer. How are you going to handle the orbit of your satellite with the LiDAR on it that is 100 kilometers by 7,440 kilometers? So does that mean you can only use the LiDAR for part of that orbit, or how are you going to do it?
Yeah. So as we have an orbit designed for 7,400 kilometers as the apogee and 400 kilometers as the perigee.
I think, Hanush, if you can reply, the other panel screen is frozen. Okay, he's back. We couldn't hear you.
I had an internet problem.
Can you repeat your answer, please?
So as we have a yes, sir.
Please repeat your answer. Okay, I think another team member may answer the question.
Hello, I'm audible.
Yes, you can go ahead, any one of you. Yeah, please.
This is Pranil here. So as you mentioned earlier, the orbit is 7,000 kilometers versus so there's a rate for which we can get.
I think can Yash or Shanush can answer?
Maybe one of them can answer a question on the communication between the individual satellites and your relay satellite. Your antennas are quite directional. Do you have the knowledge on all the satellites of the other satellites' position so that you can point the antennas in the right direction to, for communication between the satellites and the relay satellite? It's not clear to me how you handle that.
Yeah, so well. I would like to share my link for this just a second. So this is a material scheme for our mission. Our transmission scheme is basically, so basically satellites are not active.
We cannot see anything on the screen. Can you retry, please?
Okay, just a second. Yes, just a second.
Now it's okay.
Is the telemetry scheme visible? So this is a telemetry scheme for our mission. Basically, what happens is the CAMSAT, uh, it takes data and then it stores it. After that, it'll send a pulse to the relay and other satellites. It broadcasts. Basically, it's saying that the transmission will start. So other satellites are in sleep mode in terms of transmission. So it starts transmitting data to the relay. As soon as the data transmission is over, the relay sends out a pulse back to all the satellites that the transmission for the CAMSAT is over and the other satellites can continue. Then similarly, the SciSat will start a transmission and same goes for RadarSat. So they'll basically be giving out, it's like a message saying that I'm transmitting right now, so please wait till my turn is over. And when the relay, it's like a feedback system. When the relay is done, when the relay has finished receiving all the data, it sends back a pulse to everyone that the transmission is over, so the next one can send. And there are periodic transmissions. So basically, it depends on the time on each individual instrument, the amount of time it takes for data sensing. So, like for example, for CAMSAT, we'll be taking images of the surface. We'll be collecting them in a, let's say, 1 or 2 GB file. After that, it will be as the transmission scheme starts, it will start sending data to the relay. As soon as it ends, by the time it's transmitting, perhaps SciSat could take data from the mass spectrometer or the LiDAR or the magnetometer and keep storing it, and then it starts sending data to the relay. Also, we have separate storage bins in the relay so that the data from CAMSAT, SciSat, and RadarSat is not mixed.
Yeah, my question really is, do you need pointing of the antennas of the individual satellites to the relay satellite?
Yeah.
Or is your antennas omnidirectional?
These are directional, yeah.
Are they omnidirectional, the antennas?
Yeah, there's a range for the antennas. So basically, we can use the maneuver in like radio science is called, in which basically, suppose this is a source, it sends a signal. No, we don't know where the source is. So, but we have the RSSID, Received Signal Strength Indicator. So basically, the ADCS can change the orientation of the satellite in x-axis, y-axis, and we can determine the exact position of the relay, and then the transmission can start. For that, the relay will have to transmit it will have to send a beacon type transmission to other satellites.
And you will have to know the position of the other satellite, otherwise you will not know where to point your antenna.
No. For the relay, we have one directional antenna. If you can see, there's a big square plate. That's a directional high gain antenna, which will be connected to the deep space network. But we've added 1, 2, 3, 4, 5, 6 4x4 patch antennas for X-band, which will be communicating with the reconsats, which are basically CAMSAT, SciSat, and RadarSat. So there's a cone in which the field of view of the antennas, and as we have added these antennas on all the faces, we get a 360-degree view of all satellites. So there's no need, there's no worry for us that the relay can't find the satellites. It's basically the satellites have to find the relay for transmission.
Okay, can I? So thank you very much. And maybe so the on its way to Europa, maybe so the satellite or the carrier will take a very many swing by process that requires a very high accuracy of the navigation of the position of the satellite and the velocity of the satellite. How you can do that, and what is the requirement of the accuracy of the position and the velocity?
Okay, so we have ADCS systems on each CubeSat, but we need a more accurate ADCS system on the carrier stage. Also, as all the satellites are placed inside the fairing, the ADCS system is kind of inactive until we reach the Europa's orbit. So the accuracies, I've not exactly calculated it, but yeah, the accuracy is not exactly calculated yet, but we'll have to do calculations for that, like what exact accuracy is required for the maneuvering. But we can get it will, I think the approximate required accuracy should be around 0.1 arc seconds. But it's an approximation. Like we did a calculation long back, and I actually have lost that calculation. So
And this accuracy will be made by the usual RARR method, range and rate method. This navigation will be made by RARR method.
Yeah.
Okay.
So for controlling the attitude of the carrier stage, we are using a cold gas thruster system that will be changing the attitude, maintaining the attitude of the carrier stage. But for the major burns like Jupiter orbital insertion or deep space maneuvers, we'll be using the RAG engine.
Okay, thank you.
Thank you.
So your spacecraft have got quite a number of deployable items on them, notably the solar array panels. And it looks, in order to accommodate that in the launch vehicle, you'll have quite a number of folding systems and multiple mechanisms for that. How sensitive is the mission success to a failure of such a deployment mechanism?
Yeah. So if there's a failure in the deployment of solar panels, the mission is useless because we won't be able to generate the required electricity, the power. So basically we need a lot of testings on the ground so that there's enough confidence in deployment of the solar panels. We are for folding, we are using the origami techniques used by NASA and for other missions. And for deployment, basically we'll be using servo motors. So they'll be opening the solar panels that way.
Okay, we can take one more question to finalize.
Yeah, thank you. And I have a very basic question. Yeah. Could you tell us your strategy to realize the thermal control under the very limited electricity?
Sorry, can you repeat the question?
Could you tell us the strategy to realize the thermal control?
Realize the?
So how do you think about the heat balance of this mission?
The heat generation.
Thermal control on your satellites. Control the temperatures on your satellite.
Yeah. So basically, heaters could be provided in the structure. For that, we'll have to do calculations, but there are variable amount of temperatures our satellite is going because we're going from Earth orbit to Jovian orbit, and it requires a detailed, sorry, not detailed, a thermal system with a very large accuracy, but we've not done the calculations for the heat, like the heating required when it's in the eclipse mode. So we don't have the exact calculations for that.
Okay, I think we have to stop here. Thank you very much, India.
Thank you.
So the last presentation for the first session is again a video presentation from Nepal on greenhouse gas monitoring. Okay, we can start.
Greetings everyone. It's a great opportunity for us to present our paper on Earth Mission Idea Contest for multiple nano-satellites. Our paper is entitled as Monitoring the Greenhouse Gases on the Terrains of Continental Collision Plates and Warning System of Glacial Lake Outburst Floods over the Hindu Kush Himalayan region. Here are the list of our team members. We are undergrad students from Institute of Engineering, Nepal. Project outline. Climate change is one of the most important global issues right now. Not only it affects the environment, it also affects the economy and lives of the people. As climate change increases, so does the global temperature of the Earth, which is increasing by 0.18 degrees Celsius per decade. Various other studies have shown that the climate change is sensitive to altitude, latitude, and other factors. As such, mountain terrains are particularly the most susceptible environment to rapid climate change. Various disasters like outburst flood, avalanches, and landslide have a common driving force: climate change. Catastrophes like flood at Dixo on August 4, 1985, and a debris flow in the mountains of Nansel County due to the Hurricane Camille in 1969 are major examples of greenhouse gases-induced natural disasters. Similarly, the Imza glacial lake has seen glacier retreats over the years. As such, we can safely say that the mountainous terrains can be identified as early indicators of climate change. In such terrains formed by continental collision, the two major indicators of climate change are greenhouse gases and glaciers. Greenhouse gases are predominantly believed to be the indicators of climate change. Various tipping elements like loss of major ice sheets, disruption of weather cycle, and ecosystem shifts are directly or indirectly correlated to the increase in greenhouse gases. Another key indicator of climate change is glaciers. Disastrous events like outburst floods and landslide can be attributed to the climate change in the area. But at present, there is no data relating the two. Due to the lack of comprehensive and effective data, there is a data gap. The gap is what mission aims to cover. Mission of the project. The mission seems to remotely study the terrain formed by continental collision as early indicator of climate change. It aims to reduce the damage done by glacial lake outburst floods in the downstream communities. It also aims to bridge the gap between the effect of greenhouse gases and occurrence of such disaster in the continental collision terrain. The objectives of the mission are further divided into two categories: primary objective and secondary objective. The primary objective of a mission is to monitor greenhouse gases in a continental plates collision, and the secondary objective of a mission is to monitor and analyze the glacial lake in the same area.
With the necessity of the mission and recognition of the mission objectives being acknowledged, I shall further speak on how the constellation of satellites will work to obtain those. The concept of operations has been divided into three segments: the space, launch, and ground. The space segment. Our mission consists of 3 6U CubeSats in a hybrid orbit of LEO and dawn-dusk SSO. Each satellite has its own objective. The first satellite in 35-degree inclination has Hindu Kush Himalaya as the area of interest. The second satellite in 65-degree inclination collects data from other ranges such as Alps and Appalachians, which shares the same formation history of continent collision. The third satellite will be in dawn-dusk SSO, which has global coverage, and the data collected at the same time every day can be used for autocorrelation. The launch segment. Our satellites will be placed in Dhruva Space Orbital Deployer, which will be carried by Polysatellite Launch Vehicle. In the initial phase after deployment, the satellite will begin detumbling and transmit beacons for communication with the ground station. Once the satellites have been identified, further tracking can be done with two-line element set. The ground segment. Our satellites operating in S and X frequency band will perform data downlink to National Remote Sensing Center (NRSC) in India, Kyotech University in Japan, and Bird's ground station network if upgraded. The NRSC is able to command the satellite as well, as it supports both SX frequency band communication. The downlink data of the greenhouse gases can be analyzed by using Argus ground system equipment. Normalized difference water index can be applied to the raw images to monitor the change in glacial lakes. Both the raw and processed data will be uploaded to our web portal with access to all. The data obtained from this mission shall be used by various humanitarian organizations and take necessary actions accordingly. Throughout the operation, the key performance parameters in this mission are constellation and data acquisition. For the constellation part, our mission follows a Benner constellation with the addition of another satellite in 35-degree inclination. This constellation ensures the spatial coverage of the ranges formed from continent collision. For the data acquisition part, the Multiscape 100 CIS imager will be used to capture images, and Argus 2000 IR spectrometer will be used to capture greenhouse gases data. While an area is enclosed by a border, the greenhouse gases data are not, so the obtained data are very crucial. The satellite in 35-degree inclination and near polar orbit has the imager in nadir pointing for an easier plot of spatial and temporal scales. The pointing of imager in 65-degree inclination is spinning, which is necessarily a bidirectional scan mode. This scan mode ensures better spatial coverage.
Satellite design. The satellite mostly utilizes commercial off-the-shelf products to minimize the developmental cost and the errors. The satellite has been designed in an optimal way to fulfill the mission. The satellite has two payloads, the Argus 2000 IR spectrometer and the Multiscape 100 CIS imager. The satellite also has an ADCS and an onboard command and data handling system. The IADCS 400 was chosen because of its larger reaction wheels and better peak power consumption. The satellite uses an X-band transmitter and an S-band transceiver for data downlink and uplink. The satellite has two 3U solar panels on the sides and two 6U XL panels on the front and the back. The solar panels can generate maximum power of approximately 55 watts. The projected cost of the development of the satellite is less than $500,000 per satellite. Risks. The two major risks associated with the mission are its power generation and the frequency band incompatibility. Due to the satellite orientation, the power generated by the solar panel varies. To optimize that risk, the satellites in LEO operate in power optimization mode during eclipse times. Another main risk to the mission is the data downlink. The satellite utilizes an X-band transmitter to downlink the large raw data files obtained from the imager, but the ground stations may not be compatible to receive the data in X-band. Thus, the ground station networks which are on lease and support data transmission in X-band are selected for the mission. Implementation plan. The team aims to end the mission design phase halfway through 2024 and start production by mid-2026. The scheduled launch of the satellite is expected to be in late 2028, making the development time of the satellite to be around 4 to 5 years. The funding for the satellite will be sourced from various student grants and from external partnerships with related agencies and industries. In summary, there exists a lack of data in GHG-induced climate change and the subsequent natural disasters, which calls for standard procedures and data sharing for credible scientific assessments. This mission aims to meet that demand and find a plausible relation between climate change due to greenhouse gases and occurrence of outburst floods and other natural calamities in the concerned areas. With the utilization of a constellation of 6U CubeSats to monitor greenhouse gas and glacial lake data over continental collision terrain, the findings obtained from this mission could prove beneficial to mitigate the effects of the disasters. It provides a significant step in the safeguarding the well-being of the people, infrastructure, and the ecosystems in downstream communities. The successful completion of this mission will help not only reduce the potential damage due to these disasters, but also fill the relevant data gap the concerned authorities have been missing. This formally concludes our presentation. We would like to thank everyone here for their attention, and if anyone has any questions, please let us know.
Okay. Okay, thank you very much, India team. I think.
Thank you for the presentation. I just have a question about your spinning satellite. How do you plan to use a spinning satellite when you have a push broom multiscape camera? Because that camera cannot spin when imaging. What do you mean by spinning satellite? I think they're not there.
Try to connect again. Okay. Let's wait for, they are trying to reconnect. If not, we give break. No connection? Okay. They are in their place, but there is connection problem, so trying to recover. They've been reached by phone.
Hello. We are sorry for the inconvenience. We had some network issues, but now it has been resolved.
Okay. Hello, Nepal team. Please.
You mentioned that one of the satellites will be a spinning satellite. I'm just asking, how does a spinning satellite work with a push broom camera?
There might have been a bit of misunderstanding. The satellite won't be spinning. The only thing spinning will be the sensor. And the spinning sensor will be capturing images in a sweep mode, necessarily a bidirectional scan mode.
So your multi-scope camera will be spinning, is that what you're saying?
The term used is spinning, but necessarily it is a bidirectional scan mode, which is like a sweeping motion.
Okay, I don't follow your answer. Just have another question. The angle of incidence of the sun on the solar panels, you said in your paper, is a function of the inclination of the orbit. That's not 100% true. It's also a function of the attitude of the satellite and the sun angle to your orbital plane. So if you want to have more power from the sun, you can point the antennas towards the sun with your ADCS system. Did you take that into account when you did your power budget?
Yes, sir. About the inclination and irradiance angle, at first we thought we calculated it for the maximum irradiance angle, so that the angle is latitude minus 10 degree inclination. However, on further review and discussion, we calculated our power budget system with the simulation software SDK system toolkit. And with that simulation, we got to realize the maximum and minimum power generated in our satellite.
Thank you for your presentation. I have a question about the orbital design. So you mentioned that you will launch the satellites with one launch vehicle, but they're operating in 3 different inclinations. So it seems difficult to reconcile those two. So do you plan to launch in one go, or do you plan to use 3 different launch vehicles?
We have selected this PSLV deployer, this launch vehicle, so that it will be easier for us to launch our CubeSat in SS orbit, sun-synchronous orbit. However, other 2 satellites are in lower Earth orbit. They can be deployed from other deployer as well.
I see. So basically, you plan to use 3 different launches. Is that right?
Yes, 3 different. 2 can be done from the same satellites, same deployer, sorry, and another SSO can be done with the PSLV.
Okay, got it.
Space orbit deployer.
Yep, that makes sense. Thank you very much. And my second question is about deorbit. So these satellites are operating at 600 kilometers altitude. So air drag is going to be quite low. So potentially they will take a long time to come back into the atmosphere. Is that something you considered? And how do you plan to address this in your mission?
While presenting our papers or in our presentation, we have not included about the deorbiting of the satellites. But in our paper, we mentioned that there is a space for to include or sum up any extra components. So this can be another thing we can include, like for the deorbiting mechanism, we have selected this passive deorbiting technology, which is Terminator tape. We have considered this could be one of the deorbiting mechanism for our satellites.
I see.
Terminator tape.
Yep, so you still have some extra volume in your satellite, so you can add some extra systems. Got it, understood. Okay, thank you.
Yes.
Okay, thank you very much. My question is about a number of satellites. So you will launch the 3 satellites, one in SSO and one in the low Earth orbit with a 35 and the 65 inclination. So why you select the GIS orbit? And the GIS orbit satellite, only the 3 satellites will be enough for your missions?
Thank you for your question. We have 3 satellites because the first satellite in the 35-degree inclination will have HKH as the area of interest. The glacial lakes in HKH, Hindu-Kush-Himalayan region, has latitude from 25 degree to 35 degree. So the first satellite will be mainly focused on there. And as Hindu-Kush is the tallest, so the early effects of greenhouse gases can be seen there, and the possible correlation between the glacial lakes and the greenhouse gases can be done. Regarding the other continental plates collision, the maximum place at the latitude it lies is around 65 degree, which is the Urals. This is why we chose the second satellite. The third satellite, SSO, will be useful for the spatial and temporal scale, as it will be traveling over the same place at the same time every other time it revisits. Regarding more satellites, we have thought that, okay, so more satellite might be useful, but the fourth satellite will just be redundant because it will just be doing the same activity as the other satellites, but monitoring greenhouse gases and glacial lakes is not something that you need to do day by day, as it is not an immediate thing that you can see. So 3 satellites will be enough, and that is the reason we also chose the different inclinations.
Okay, thank you very much.
So we can have one more question if you.
Why do you have different momentum storage capability in the 3 axes of the satellite with the 3 wheels? You listed in the x-axis, this is the momentum storage. In the y-axis, that is the momentum storage capability. In the z-axis, another number for momentum storage capability. Why is it different between the 3 axes? The momentum storage of your reaction wheels.
Actually, that's the maximum capability of the IADCs that we've used in the system. It's not, we've not specified any momentum capability of the ADCs, but that's just what's been available for the payload.
Okay, I think we have to stop here. Thank you very much, Nepal team.
Thank you. Thank you.
So now we have 20-minute break. Please be back at 15:39. Thank you. Okay, ladies and gentlemen, we have to start the next session. Please take your seats. Okay, we have another video presentation from Bangladesh, BREC University, and the topic is use of nano-satellite constellations to identify coral reef cultivable areas on the seafloor. Okay, I think we can start this.
Greetings, esteemed audience. My name is M.A. Muntasir Abtahi, and I am currently pursuing my studies in the field of computer science and engineering at BRAC University, located in the beautiful country of Bangladesh. And these are my teammates. Today, we will be talking about how we can use a constellation of satellites to identify coral reef cultivatable areas on the seafloor. To begin, we need to know what is coral reef and why are they crucial to our environment. Coral reefs are the most diverse marine ecosystem, supporting a vast range of marine life such as fish, invertebrates, algae, and so on. That's why it's known as the sea's rainforest. They are also an important environmental indicator since they are sensitive to changes in water temperature, salinity, and pH. Because these reefs are so important to our ocean and our world, they must be protected. They are also economically significant since they support fishing, tourism, and other industries. Not only this, they also contribute to the global carbon cycle in a complex way because they can capture, accumulate, and release carbon in various forms such as hydrocarbon, carbon dioxide, calcium carbonate. They have 26 billion tons per year contribution to the global carbon cycle. They also offer a living for 13% of people who reside within 100 kilometers of the coral reef. Most notably, coral reefs have a 32% of medicinal and scientific value. Now I will tell you about the constellation mission objective. We have three key goals and they are tracking and monitoring the coral reef with a multispectral camera, and using the data we will identify optimal environmental conditions in which the coral reef can thrive perfectly. We will investigate different areas for coral reef rehabilitation after determining the ideal environment model. We also have a secondary goal, which is to use microcolony fusion technique to boost coral growth in the new location. Upon achievement of these objectives, we will be able to engage stakeholders with different international organizations such as UNDP, UNEP, Coral Reef Alliance, Coral Guardian, and others. To achieve the goals, our operational concept has been partitioned into three distinct components. During the launch segment, we will discuss the constellation layout, the number of satellites, and other relevant matters. The space segment, during which we shall discuss the objective of space mission and its satellite components, and the ground segment, during which we shall discuss the planning of our ground station and data management data flow. First of all, I would like to talk about the ground segment. There are numerous open source coral reef dataset available. Some of them are open source information system, coral reef information system, coral reef based ocean color. We will use them as a ground truth. Our satellite will transmit information to the ground station data. The data will be preprocessed by the ground station in a variety of ways such as cloud and cloud cover correction, water column correction, masking, radiometric and geometric correction, light scattering correction, and so on. Then we will combine ground truth and satellite data to produce a data fusion. And using the support vector machine, develop an object-based image analysis model. We will additionally create a geomorphic map of as an output for geo-visualization with all relevant factors. With the help of the model, when our satellite sent us an image of a new place on the sea floor, our model can determine whether or not the environment is suitable for coral reefs. If the habitat is habitable, our model will tell us which type of coral reef can be restored there. What environmental factors will be sufficient or significant for the coral reef that will be present there. Let's talk about the orbital parameters of the satellite. Because we need to photograph coral reefs, we will choose a sun-synchronous orbit. Our constellation will form a linear formation together. A total number of 14 nanosatellites will be in the constellation. The swath width will be 55 kilometers per satellite. The temporal dimension is 5 days, which means that our satellite will return to the same location every 5 days, and the altitude ranges from 750 to 770 kilometers above the sea level. Let's have a look at the technology that powers the nano-satellite. We used all commercially accessible items including the structure, transceiver, onboard computer, electronic power system, cameras, solar panels, batteries, propulsion system and ADCS. Coral reef mapping can be mapped through different processes. We have planned to map coral reef in a way thus we can get a time series model along with the sea surface temperature, NDVI, NDWI, coastal and aerosol data all together. We will also try to find the relation between ocean wave and the coral reef habitat. One of the important measurement factor is sea level swell condition. We will also map the habitat with the image processing. Keeping all these mapping parameters together, we can generate a model. For our nano-satellite, we have created a simple architecture. We have an onboard computer and a communication via S-band transceiver and a S-band antenna. We have an electrical power system that is linked to the solar panels. We used a sun sensor, reaction wheel, magnetorque, altitude feedback and barometric sensor as a ADCS. Every component is connected with the bus interface. Our main payload is Mantis Dragonfly camera, which is also commercially available. As we are employing a 3U nano-satellites, we are also using a propulsion system. Now let's talk about the key performance parameters. Within the generated power, the maximum power consumption is 55% and average power consumption is 23.3%. There are other key performance parameters like our image size is 5.5 km square with the spatial resolution of 10 meter. Our delta V is 100 meter per second. Our battery pack is 45 watt with the average power consumption of 10.5 watt. Now let's talk about the implementation plan. Before implementation, we have to briefly outline the purpose of the launching and satellite, and we need to make a plan of tracking and monitoring the coral reef. Highlight the utilization of remote sensing term to track changes in coral reef. We also keep in the mind about the activity plan and the budget plan. We also have some strategies against the risk. Let's look into our approximate budget. Here we can see our total budget is 13.4 million USD. Where the space launch segment will have 59.7% of our budget and unit flight model will have 31.3%. The other will contain prototype, ground segment, environment testing, unit flight mod, engineering model and so on. Let's talk about the risk management. One of the risks is solar panel deployment. If the solar panel doesn't deploy, there will be insufficient power generation. We can solve this problem by conducting through testing and simulation. Our camera need to be calibrated as we will be operating in a new environment. So we need to implement an advanced camera calibration algorithm with our onboard computer. There might be a delay of launch or license. To mitigate this problem, we need to initiate the licensing process early, and that's the only solution. Let's look into the project schedule. We have divided our project schedule into 5 different sectors: mission definition review, preliminary design review, critical design review, flight readiness review, and the final practice operations. That takes me to the end of my presentation. To attain this objective, we must first have a thorough understanding of coral reefs. Underwater living organisms have a very significant sustainability aim, and we are extremely glad to include that purpose into our project. Again, create technology by creating organisms of coral reef that can evolve in response to their surroundings. Every project has some risk, and we have certain risk mitigation technique in our project. We have compiled data from various sources, which we present here as our reference. If you have any inquiries or ambiguities, please consult this prior reference. Everyone, thank you. Thank you very much. If you have any inquiries, we would be incredibly honored to provide answers. Your gratitude is appreciated. Thank you, guys. Thank you, everyone.
Okay, thank you very much, team. Please.
Thank you for the presentation. In your paper, you said that 14 satellites will be launched independently to avoid potential hazards. What do you mean by that? I mean, to launch independently will cost a lot of money because you have 14 different launches for 14 satellites. Why do you have you decided to launch independently?
We actually plan to improve our satellite each and every steps. For the first launch, there are some risks for to mitigate the risks. We have to launch them separately. For that, we have to get the idea that we have to launch them separately or independently.
What is the altitude you've chosen for launching your satellites? Because in the paper it's very confusing. You said that initially it will be 750 to 770 kilometer orbit. Then you said it's 600 kilometers sun synchronous. And then you said 500 kilometer orbit. Which one is it? Did you follow me? You're not clear in your paper about the altitude of your orbit, the final orbit.
The final orbit will be 750 to 770 kilometers.
Okay, thank you for your presentation. I have a question about the inclination. So most of the corals are located at quite low latitudes. So in one sense, it would make sense to use an equatorial orbit to maximize coverage. But in this case, you're using a sun-synchronous orbit. So I'm curious why you decided to go for sun-synchronous instead of equatorial.
Our camera is a passive sensor camera. So if we use the sun-synchronous satellite, we will get the proper radiation from the proper sunlight and get a proper output spectrum. That's why I've chosen the sun-synchronous sunlight orbit.
Okay, thank you.
Thank you very much. So would you tell me a little more about why you choose 7 satellite or 14 satellite constellation? So maybe the number of the satellite in the constellation should be decided to consider how the environment or situation will be changed. So would you tell me a little more about that?
We have seen this way that coral reef have a decaying factor of 7 days. Like after the 7 days, they have some changes in them. So we need to our temporal resolution less than 7 days. That's why we have chosen 14 satellites so that we can cover it within 5 days.
I have a question about the barometric sensor. So you mentioned that your satellite is equipped with a barometric sensor for attitude determination. I'm curious how you plan to use a barometric sensor for that purpose. Right, so to my understanding, there's almost no air at 750 kilometers altitude, and yet you're using a barometric sensor. So I'm curious, right, how that fits into the mission operations.
I think if they have just came to knowledge that there is no air at 750 kilometers, I just forgot that time. So there won't be any barometric sensor. That's maybe a fault. That's a fault. I'm sorry.
Okay, understood. Thank you.
To calculate the battery power requirement, you said it's 45 watts. Normally, you specify the battery capacity in watt hour. Why did you choose the watts as a unit there for power? Batteries are energy storage devices, so you can say they can supply so many watts in an hour, and not just the watts. That's just the peak power they can supply. So the unit you're using
yes.
for your power analysis is not right.
Yes, we just used the power rating for battery, and we calculated just for per hour.
So you require peak 45 watts from the battery. That
Yes,
doesn't
yes.
specify the capacity of the battery, how big it should be, because you can supply 45 watts from a penlight battery for a very short period of time.
Not short period of time, but it's the peak power is 45 watt.
Okay, thank you. Would you tell me a little more about the requirement on the ADCS? Yeah, requirement for ADCS. So how much, for example, the attitude control accuracy will be required, or attitude stability will be required?
We required our image should be clear, and our camera should capture a clear image. So we will use our ADCS as to maintain the sun synchronous orbit and to keep it at a altitude of 750 to 770 kilometers. And if you are talking about some kind of accuracies, I'm sorry, we didn't calculate it yet.
Okay, so please calculate that. That is very important. Okay?
Yeah, if you want to image a target and your swath is just 40 kilometers, you must make sure from 770 kilometers you will be at least pointing within a couple of kilometers to the target. Otherwise, you're going to miss the target in your pointing. So there must be a pointing accuracy requirement as well as a stability to tell you how clear the image will be.
Yes, we just assume it.
As we are in person, we on we is a lot of things for so we assume.
We couldn't understand you. I mean, the transmission was not continuous.
Being beginners, we assume the thing.
We have assumed some things, and we have researched something, and based on our research, we have assumed something to come to a conclusion with the plan.
So maybe one important consideration is what happens at the end of the mission. If you're operating at 750 kilometers, there's not much air available. So if you leave the satellite without any further action, it will stay there for a very long time. So what do you plan to do at the end of the mission for space debris mitigation? Do you have any plan for this at the present moment?
No, we don't have any plan for this at this present moment.
Okay, right, but probably this will be quite important as you continue to develop the proposal. So I'm looking forward to that, yeah.
Yeah.
In your cost budget, you list cost for the engineering models and then the unit flight models, and they're relatively comparable. You also list the environmental testing of just a one-off event. So does that environmental testing only apply to the engineering model, or would you be running a separate test campaign, an acceptance test campaign, perhaps for all 14 spacecraft? Or to ask the question conversely, what is your non-recurring engineering amount? Is it quite heavy or very light?
We will select all components from the market, like they are commercially available, and we will select them as all the models number, like at the batch number are same. Then our costing will be less for one testing, for 1 or 2 spacecraft testing, but rest of them won't need to be tested because they are from the same batch.
Okay, I think we have to stop here. Thank you very much, Bangladesh team.
Thank you, sir.
Now we are back to inside presentation. The Thailand team from UNISEC Thailand. Specify animal's location via sound, please. Okay, please start.
So, can I start?
Please.
So, hello everyone, we are UNISEC Thailand, and we are our team. So, SOUTH is a cloud-based conservation mission focusing on updating data for the remote forest as fast as possible. So, these are the content for today. So nowadays, the technology that used in the remote forest area is a tapping camera, which obstacle in the line of sight, the sizing data, and the short lifetime are limitation. But if we use the sound as a detector, although we will lose the visualization, but the limitation can be eliminated. And it will be easier to protect and preserve the wildlife from the poacher, locker, and animal trafficker. And with satellite communication, we are able to reduce the recovery time from 0 days to an hour. So our mission have 2 main components, both on ground and in space. On ground, we have the data alert and data hub, and in space, we have data set. So elsewhere, pinpoint hopping, Malaysia lapin, and white water buffalo have been chosen to be animal interest due to endangerment and surface of sound. All of them can be located in Hoi Keng Wildlife Sanctuary, which on the western side and is the largest wildlife sanctuary in Thailand. From the information that we have by the head of wildlife sanctuary, we are able to locate 5 different areas where are the habitat of our animal interest, and total is around 1,270 square kilometers. So our objective is try to locate the animal by its noise, try to specify the animal by using the AI, and we want to lighten the workload of any forest officer. Our concept of operation, like I said before, we have components both on ground and in space. So the alert will be recording and analyze the sound, and then send it to the hub, which we will relay it to satellite, and the satellite will be relayed information to the ground station. So the blue one is the alert, the yellow one is the hub, and the blue one is the sat. So the information that is will relay onto the city where they have internet is going to be sent it to Department of Nature Park in Thailand. So this is our design for the alert. So the component you can see on the left hand side is basically like the satellite, but we attach it in the forest with the tree. So this type will is on the lightweight design because we have to attach on a tree, and it will be able to touching the harsh environment in the forest. And the material have to be non-toxic to the nature because we're doing with the wildlife. And the important one is it has to be cheap because we use it more than 1,000. We aiming it about $1,000 per direct alert. And this microphone is capable to recording the acoustic frequency that we want. It has low power, it's able to touching the harsh environment, and it has been used to this similar application before.
And for this topic, regarding the LoRa network, we utilize the Radiohead packet radio library to establish the network between the TerraTech alert. We designate the TerraTech hub as the gateway. For the layout of Teletech alert, we have evaluated and scored each design. The route layout stand out as the top ranked option, deemed most suitable for our mission. And this is the component diagram of Teletech alert. Teletech hub is installed in the area number 4, which is close to one of the national park posts. The first challenge is the density of the forest, posing an obstacle to communication. The second challenge is the difficulty in accessing electricity, requiring the use of generator for the Teletech hub. We train our artificial intelligence using the recurrent neural network method from record sound. The process involves the following step. First, we convert the audio wave into a frequency by using the fast Fourier transform. And next step, then we copy the frequency, would be make one of them would go through a low pass filter and other one would go to a high pass filter. Next step, we extract variant important feature from both formats, such as maximum and minimum frequency value. Next step, we train an AI model using the field data. This involves teaching the model to recognize and classify different animal sounds. And the key performance, there are the precision of the artificial intelligence. F1 score we call accuracy percentage and number of correct prediction. And there are the prediction results generated by the AI. In addition, we also monitor variant other metrics, including MAE and RMSE. And for the implementation plan of ground segment, we have test communication and assembly and install. Last one is increase the database for AI.
Please see from right to left. Usually, Teletech set will work in a normal mode, which transmit telemetry data by using continuous wave beacon every 5 minutes. As soon as the Teletech set passes over the Teletech hub, it will turn into alert state, which receive 3 calling data, and then when the after that, the Teletech set will turn into mission stage, which transfer the confirmation signal and receives all mission data from all Teletech hubs. And lastly, as soon as the Teletech set detects the ground station in its transmitting range, it will change into a downlink stage and transmit all stored mission data to the ground station. However, at any time, as soon as the Teletech set detects its internal voltage lower than 3.5 volt, it will turn off every subsystem and change to safe mode. The constellation of Teletech set will be sent as a set of 8 satellites in low Earth orbit, since it allows satellites to communicate efficiently with low power and also more cost efficient compared to geostationary orbit. At an altitude of 500 kilometers, the period will be 1 hour, 34 minutes, and 36 seconds. And Teletech set will have a longitude of ascending node 45 degrees to each other for we can make sure that every time, at every single time, there will be at least one third track set over the third track hub. The estimated lifespan is around 3 years. After that, the third track set will decay and re-enter the Earth's atmosphere. Our implementation plan is to send a new set of third track set to continue the project. And as we still have the permission from involved organization.
Next is the key performance to drive the success of our projects. For ground segment, it is the communication and detection range of this third track arrays. And for space segment, it's required from the third track set. Next is risk management. So as you can see from this slide, I prioritize the risk by its color. The darker color is the greater issues. And in conclusions, our project is doing for wildlife conservation. And it's not only...
Please conclude. Conclude.
Okay. Okay. So can I start from the... Okay, for conclusion. Okay, so our work is for wildlife conservation by using the third track set that have the voice detections and the AI analysis to estimate the location of animals, and use the third track set to overcome the challenge of remoteness. And also, this device is not only using for tracking the animals, but it also boosts the effectiveness of animal monitoring by using with other form of monitoring. This is all. Thank you.
Okay, thank you very much.
In your paper, you said you've got 8 satellites, and they will be launched in different orbital planes. So that means there's 8 different launches required. That's quite expensive.
So for this question, our plan is they are in the same incarnation, and when it's done it, we try to make it inside only one launch, and it's, as a note, it will be different. So we want to let it overlap on the overhaul camera essentially over time.
So your right ascension of ascending node will drift over time differently for the satellites.
Yeah. But in that part, I have to a bit more with like the calculating, because for the number and some of the practical, we don't sure that how to read, but I think we need some more knowledge when we.
Yeah, so I think you need to investigate that a bit further. Your TerraTrack hub will communicate with the satellite,
yes,
but without any tracking antenna. Your ground station have a tracking antenna to track the satellites, but not the TerraTrack hub.
The hub doesn't receive any information from the satellite. It's just sending up.
Yes, but you need to do a proper link budget there to make sure that you can receive enough signal on your satellites.
Okay. Thank you.
Yes, I have a similar questions. So you already calculated how much data will be received by the satellite, and that can be downlinked to the ground. Such kind of the data management calculation is done.
Can I have the last word again? Your last word.
Yeah. Data management calculation. How much data will be stored on the satellite, and all the data can be downlinked to the ground. Such kind of the data management.
So the data management that we calculate about is roughly about one megabyte. One megabyte. Sorry about it. And by this number, with our data set, they will have some data that we didn't send up to it, because most of the data that we send is only the file data. So somewhere else they don't file anything, because we recording the sound over there, and we know that it's gonna be the massive data to manage. So we try to reduce it and encrypt it, and using some symbol as maybe one meaning file, not the full word.
So you say 1 megabyte per one satellite per day?
Per orbit. Yeah, this is the maximum maximum that it
1
able to get.
megabyte per day.
Yep.
And so your communication system can downlink that amount of the data to the ground every day, right?
That is it, the point that we have to do it.
Okay, have to do it.
Have to do it.
Okay, the second question is that you are using the machine learning, you know, the DNA or something, and how you can get the training data?
So the data that, some data that are available in the internet, because this endangered species is able to find a bit, and some of it is in the zoo. You can go to UNO zoo, you can find the medicine lapin over there, and yeah, we can use some of the data to training our AI.
On the website, you can get sound data.
Yeah, and it have the organization in the German that I found that they doing with the acoustic sound for recording this type of data.
Okay, thank you.
Many animals are quite silent, like wild cats. They don't make noise because then their prey runs away. So anteaters, rhinos, they're very quiet animals. How do you aim to detect them?
So that's why we choose our interest, because first thing that we have to looking for the endangerment, and the second thing is the sound. You can see that we selected bird, they pinpoint hobbit, they very endangered, and the white water buffalo, they also make a sound, and the massive is you quite not usually heard sound, but it's very in the high frequency stuff. And the LCR, the point that we choose LCR because the LCR is, although it's in the Thai law that we have to preserve it, but they have some like they creating. So it's like they have some zone that is they found that it's going to be here. It's exactly in this zone 2. That why we should them to be like our tester.
And also we have used this information to talk with the head of the wildlife sanctuary, and he said that it can be the possibility to track this animal by using sound.
Why do you need satellites for this mission? Why you're only using satellites to take data from TerraTrack Hub to the ground station. Isn't there other cheaper ways to do it? Cell phone signals or drones?
So in the farthest side, like the zone A1, A5, A4, and the side of A3. So it's in the deeper forest. You may take about 3 days to walk into that, and if of course you don't have internet inside the wildlife sanctuary. So yeah, it's this kind of question I face it a lot, and our benefit of satellite is you cannot like go in there and recover the data from your camera every day, because it's a bit too hard and really risky that you walk into the forest by yourself, and maybe you can attack by elephant, tiger. So that's why we satellite.
Yeah, but your TerraTrack Hub is collecting all the data from the sensors. You don't have to go to the sensors. All the data is sent to the hub. You only need to get the data from the hub to your ground station. Isn't there other way to link the hub to the ground station than using a satellite?
So if we link it outside, maybe it's gonna be in particular zone is have very high strict lesson that you have to ask them before you get into it, and for when you want to put it on the outside, maybe it's have to invest more space to do it, and that is will affect the cost. Because for now I invested the cost maybe about $7 million about, and it able to be go up, because if you want to do it with the whole wildlife sanctuary, you need to take a much more data alert into it. And using a satellite, I think it's edge on the time that you can get. It's about 1.5 hours in every day. And if you link it to outside, maybe it's have to be a bit farther and more complex.
So the satellite is basically only active when it's above Thailand and above the national park. So for most of the orbit, it's not doing anything. So have you thought about combining this mission objective with some other activities to try to increase the activity over each orbit? And in that case, maybe it will be more attractive to use a satellite.
So our case, actually, the satellite have one payload. So that payload is, if it has possible way to send a payload with the other satellite, yeah, the cost will be down, and it can be, after we doing it in Thai, maybe you can do it across the world, because this orbit is across the Amazon, is also across the Japan, and maybe somewhere in Africa. So yeah, after we doing this, maybe we can able to do it across the world, and it will be easier to attach the funding.
Okay, we have to stop here. Thank you very much.
Thank you. Thank you.
Now we have a team from Japan on tsunami forecasting, Masashi Kamagawa from University of Shizuoka. You can start, please.
Okay. Hello, everybody. So I'm Masashi Kamaga from the University of Shizuoka in Japan. We've collaborated with Professor Yamazaki and his student in Nihon University. So today, we are talking about the tsunami early warning system using the CubeSat. Then, at first, I introduced in the largest disaster of the natural disaster for the last 20 years, like this one. So you look at this one. Earthquake inland is the largest disaster. But also, similar percent, tsunami is also serious. This is serious. So I think earthquake and tsunami is quite severe for the natural disasters. In particular, tsunami is this is a focus for our talk. Then, look at this figure. So this is the mechanism of the tsunami. So maybe everybody knows how to make a tsunami. So there are two plates. The two plates, one plate is the push and the dragging, and so the upward in the land in the push the water. Then tsunami is created. This is the typical how to create in the tsunami. Then, the current the tsunami early warning system in Japan. In Japan is this advanced and tsunami early warning system countries. So at first they issued, they determined hypocenter and magnitude from the seismic wave, and up to the 30 seconds. Then they determined the angle of the faults, and using also seismic data. Then they issued the tsunami. Then they calculated already the various epicenter and various magnitude, and various fault plane angle in advance. They calculated tsunami wave in the database. Then when we determined in these values, they pick up the estimated or the possible the tsunami magnitude, then issued the tsunami early warning system. But this system is very fast, but lots of uncertainties. So if we believe this one, somebody died from the wrong informations. This is quite serious issue. This is one of the examples in the Tohoku earthquake in the 2011. This is 3 minutes after the earthquake. This earthquake occurred here. This is the Japan Meteorological Agency issued. So we have the red color, the orange, and the yellow. This indicates alert level. This is 3 minutes later, but estimated magnitude is 7.9. This is quite small. Real magnitude is 9. So this is after the analysis. Then, this is the underestimation. It means more than 40 times the underestimations. This is the 28 minutes. So this is already some of tsunamis arrive at the coast. This time is JMA, Japan Meteorological Agency, estimated in the 8.8, still small, because real magnitude is 9. Because one magnitude difference is 30 times energy difference. Then this is one of the good, one of the intriguing result. This is the identified magnitude. This is the elapsed time from the after the main shock. So the second. The first 10 seconds, so they estimated in the magnitude in 5 or 6 from the seismic wave. But so after even 1 minute later, their estimation is 8. 8 is small. Small is 30 seconds, the smaller than the real energy. Real one is a magnitude 9. So it means that this is the underestimations. So this is they give the wrong information. It means the small tsunami arrival. But some people died. In Tohoku earthquake, 2,000 people died. The wrong information. So look at these figures. This is a tsunami simulations. This part is a fault plane. The fault plane push the waters. The push the water is like here. The initial tsunami source is created. Then tsunami propagated in this direction. If we want to the accurate tsunami simulations, we need initial tsunami height. That is most important to the accurate tsunami issues. Then, but so far, nobody knows, nobody can measure the initial tsunami height. That is the most important. Of course, if you stay here, like bird, in the monitor here, well, you can understand the exact initial tsunami source, but no one do that. That reason why this is a serious. The wrong information is from the wrong information. This is summarized of why the tsunami forecasting is difficult. One is the estimation is magnitude is very difficult, up to the 8. The next one is fault plane can push the waters, but initial tsunami height is quite similar to the fault plane in the upward. But this is not always coincident. Because sometimes in the landsliding over the ocean occurs, so the initial tsunami height much higher. That is the reason. Last one is this is the largest reason. There is no direct measurement of the tsunami source. So we need tsunami source. That is for the accurate tsunami observation. So in order to solve these issues, so we focus on the space measurement. So space is good, so because we want to see the initial tsunami height in the various one. This is a method one. I discovered very important phenomena when it was the Tohoku earthquake. This is one of the reasons. Tsunami pushes the acoustic wave. They are propagated into the ionosphere. Then ionospheric electron decreases after the tsunami. This is ionospheric electron contents profile. So this profile is quite similar is initial tsunami height. I discovered this phenomena. So I noticed that if we measure electron contents, electron distribution of the hairs, we can know initial tsunami height. So this one. So in particular, if we have the constellation of the low Earth orbit satellite, so if we apply in the GNSO radio occultation, we know this kind of the 3D distribution of the electrons. Then next one is, this is also interesting phenomena. We call it the method 2. So that this is the, you know, the AIS, you know the VDES. So we can get the ship data from the various the ship all over the world. Then so we can get the data, ship data from the satellite. So ship data includes direction of the ship and the ship velocity and some kind of things. So once tsunami propagates into the ship direction is changed. So we can understand the tsunami velocity from the ship informations. So my friends, one of the friends, discovered this kind of the way. So if you get this kind of the ship information from the all of the ship, so we can estimate the tsunami velocity, and so from the inversion calculations, so we can estimate tsunami source from the ship data. Then last one is this is a GPS RO. This is also some kind of similar way. So the GPS RO, the reflection of the GPS signal. So we received this kind of things. Then so we can estimate in the tsunami. Then this is a summary. So we can apply the three methods, and so the real-time communication to send the information. We use the Inmarsat. This is the CubeSat. So CubeSat is 6U. Then this is so we use the 6 degrees inclination. So then this is the important thing that we applied the fading methods. So we know lots of the constellation of the satellite all over the world. So once we released the 10 satellites with different velocities, so we operated 6 months. So it means the satellite distributed like this one. Then finally, so the 6 months later, we can put the uniform distributed satellite all over the world. So this is the important cost budget. So if we apply this this operation for 2 years, the 2 years almost $6 million for 2 years. But so this is the recent Japanese government tried this one, and they put the ocean bottom cable with the tsunami gauge. This one is very expensive, but effective. But so if we put this globally, this kind of the ocean bottom cable, it costs in the 40 billion per 30 seconds. If we apply this satellite method, it's much cheaper, 6 billion. Then we can forecast in the tsunami, the globally. That's all. Thank you very much.
Thank you very much. Please.
Why can't buoys floating in the water, in the sea, not tell you the way, the height of the water, the change in height of the water?
Why?
Yeah,
No.
why? Why can't buoys give you
What do you mean buoys?
Stuff floating in the water, sensors?
Yeah.
And they tell you with GPS exactly the height of the buoy.
Yeah.
At any point in time. And you can get that information fed back to a ground station somewhere.
I'm afraid that I misunderstand the questions. Let me repeat the explanation. The fault move like this one, they push the waters. So we have the initial tsunami height. If we have the initial tsunami height, we have the accurate simulations. So it is easy to exact accurate data of the tsunami propagation. But so of course, seismic wave is determined push the upward of the fault formations. So if we can estimate this kind of fault formation, but the fault formation is not corresponding to the initial tsunami height, because sometimes landsliding in the ocean, bottom of the ocean occurs. So it generates much more enhanced in this push the waters. So it means the Toka earthquake is this kind of things. The landsliding is also occurred, and the push the fault is also generated in the initial tsunami height. Can you understand what I said?
But I believe you.
Yeah.
Just another question.
Yeah.
You said that you release your satellite at different velocities.
Yeah.
And that gives you different heights in circular orbit. That's not true. The height where you release your satellites at different velocities is exactly the same of all the satellites. It's just the apogee that will be different.
Mm-hmm.
So you need to do another thrusting maneuver to have different orbit altitudes between the satellites. An initial difference in speed doesn't give you a different circular orbit altitude.
Of course, so we changed the attitude and also the solar panel directions to control in the velocities up to the 6 months to diverse in the whole satellite. So we don't have the maneuver in this case. So we follow this way in the, for example, signal satellite. So I think many satellites apply this kind of fading method.
Yeah, you can use drag to change the orbit.
Yeah, right.
But that takes time. It's not instantaneous.
So we need 6 months. Yeah.
Okay, so thank you very much. And maybe as you know, that the Spire Global has a lot of constellation which can obtain the radio occultation measurements. So is it possible for you to utilize such kind of the data for your prediction?
Of course, we can use it. Also, we can supply this kind of the radio occultation data in the other purpose. For example, meteorology and space weather, many things. So that quite useful for this kind of data. Of course, we can use the other satellite data, as you mentioned.
Thank you for your presentation. So most of the time, there will not be any tsunamis, and you will be collecting data on speed of the ocean or ocean height. So do you plan to use this data for other purposes in addition to tsunami prediction?
Please repeat this question again. Yeah.
So the satellite constellation is used to study tsunamis.
Yeah.
But most of the time, there are no tsunamis. So during that time, do you plan to use the data for other purposes?
Of course. As I mentioned for the Professor Nakasuga the questions, so we obtain the distribution of the ionospheric data. This is useful for the space weather. And also we have the radio occultation. Radio occultation gives the meteorology information. So some of the former satellites use this in the meteorology forecast already. Then so we can use this data in the meteorology and forecasting. Many things.
In your paper, you have a couple of equations showing structural analysis of your spacecraft. And the frequencies there is totally too high, unrealistic if you have deployed solar panels. Deployed solar panels bring your resonance frequencies to quite low values. And that's not reflected in the paper. Also, the thermal analysis in your paper is very simplistic. It's not very simplistic. Yeah, it's first order.
Yeah.
It's not accurate enough. So it's just observation from my side.
We are very sorry to the not accurate our calculation.
Yeah, it's a first order. It's a first order estimate, but it's not really useful. But the structural analysis, definitely, the frequencies of 1,000, 2,000 hertz is for a compact satellite without any deployables. As soon as you have a deployable, your structural frequencies come down a lot.
Okay, thank you very much. So our calculation is not enough. We understand this kind of thing. Thank you.
For the use of the AIS data in the boats for sea traffic. So
sea traffic? AIS, okay, yeah.
So you'll use a combination of position and velocity data.
Yeah.
For that, this AIS element of the calculations, how big a proportion is that into the final calculation, and along with the question of what's the time resolution in the AIS data, because to measure the velocity and the height.
I think, of course, there's some of the vessel transmit in 1 minute or in the 10 minutes. The data of the AIS, but so most of the vessel has 1 minute resolution of the observations. Then let me explain how to measure the tsunami from the AIS. So once in the propagated in the tsunami like this one, then we have the ship then the tsunami and the change the ship direction and also the velocity. Then we can recalculate it how velocity the propagate into the vessel. Then we can understand the tsunami velocity at this point. Then if we have this kind of tsunami velocity point, we can calculate the initial tsunami source by using the inversion calculations. This is a quite simple way.
Okay.
This is applicable. Yeah, applicable. Yeah.
Okay, we have to stop here. Thank you very much.
Thank you very much. Thank you.
So our next team to present here is Cubes AI from Middle East Technical University, Turkey. Okay, you can start.
Good afternoon, everyone. This is İpek Elmas. Welcome to the presentation. Of CubeSat, CubeSat-based sensing and AI for disease prediction. We are attending from Middle East Technical University, Ankara, Turkey. Here you can see our team members. We are all undergraduates, aerospace engineering students. These are the topics that we will discuss today. Beginning with the introduction, vector-borne diseases are human illnesses caused by parasites, bacteria, and viruses that are transmitted by vectors. Malaria, dengue, and plague are a few examples of vector-borne diseases. Vector-borne diseases causes more than 700,000 deaths every year, and 80% of the world's populations are at risk of one or more of them. Our primary aim is early detection and prediction of vector-borne diseases by using technologies such as remote sensing, geographical information system, and artificial intelligence. Why do we need this project? Because, first of all, studies prove that climate has a direct impact of transmission of vector-borne diseases, and we need to investigate the origin of vector-borne diseases to detect and predict it. Here, you can see the effects of the climate change on the spread of vector-borne diseases. Secondly, scientists found a co-infection between COVID-19 and vector-borne diseases. Apparently, environmental factors such as humidity, air transmission, and temperature affect the transmission of COVID-19 as well as vector-borne diseases. However, this specific subject remains relatively unexplored in academic circles, so we need further investigation. Continuing with mission objectives, our primary objective is to detect near real-time data and create a risk map for vector-borne diseases. Our secondary objective is to obtain weather data in severe weather conditions using SAR within a 6U CubeSat. And our third objective is to gather data despite spatial and temporal constraints and process and interpret it using AI.
Hello everyone, this is Alper Güvercin speaking, and let's continue with the concept of operations. As you see here, we have two types of CubeSats in our constellation working as pairs. The first type of CubeSat is CubeSat-A, is a 6U CubeSat carrying a payload of active remote sensing sensor, namely SAR. And the second type of CubeSat is CubeSat-P, which is a 3U CubeSat carrying a payload of passive remote sensing sensors, namely hyperspectral camera and microwave radiometer. And here you can see the rough CAD drawings of our satellites. This CAD drawing belongs to RainCube, which is a 6U CubeSat carrying a radar. And our CubeSat-A will look like this, so we put it here. And I don't know if it caught your attention, but we only use remote sensing sensors, and we separated them as active and passive. The thing is, we are using remote sensing devices because they are the best option to Earth observation missions and tracking diseases with satellites. And if we come to why we separated them as active and passive, as you can see here, their operating conditions are different. That means they are being affected by different conditions, such as weather conditions. For example, while passive remote sensing sensors cannot properly work under cloudy weather, active remote sensing sensors can. And on the other hand, power consumption of the passive remote sensing sensors are lower than the active ones. And now we can continue with the ground segment. As you can see here, we have a master ground station and local ground station. Starting with the master ground station is located in Ankara. And the local ground stations, we have 3 local ground stations located in prone to vector-borne disease countries, which will be conducted with cooperation with the local universities. It goes like satellites will downlink the data to local ground stations, and then they will send it to our master ground station. And in the master ground station, AI will analyze the data and report it. And next, you can see our rough Gantt chart here. Our plan is to start developing our systems by January 2024, and we want to start our mission by July 2025. Of course, this is an optimistic approach, optimistic timeline, but with the help of the local universities, as I mentioned before, and the help of other organizations such as our sponsors, Plan S, we think that's possible. And now we can continue with the mission operations after deployment. Let's start with the early operation phase. As you can see, we have 2 different early operation phases for CubeSat A and P. CubeSat A includes a SAR, and the mission operations of CubeSat A will start after the activation of SAR. Then, if we come to CubeSat P will start its operation after the calibration processes. Then, nominal mission and history of the CubeSat begins.
I'm Yunus. I'm presenting the key performance part. We choose SAR, as previously mentioned, to its high coverage and high resolution data rate, and since we need it for our mission, but we need a minimized version of regular SARs. And we will need a minimized power consumption to fit in 6U CubeSat standards. And you can see the SAR's antenna, internal specifications of it. It will use the X-band and the sweat width with 350, I guess, kilometers. And next, the data transformation part. Since we are downlinking some various and much data from our satellites, we need to properly adjust the ground segment. And we will use the data collected from the ground on Earth by the organizations such as WHO and other open source vector-borne disease databases. We will use the GIS system for our satellite data, and we will store them with our georeferencing and field verification systems in our ground stations. And next, this is the space segment part. Our payload, the first 3, the telecommand and telemetry, and onboard computer and also a DCS system can both be used in our CubeSat A and CubeSat P. And next, hyperspectral camera and microwave radiometer is CubeSat P's payload and SAR. And we will choose commercial off-the-shelf solutions for our satellites since we to minimize our timeline and also secure the mission and do it more securely. And yes, this.
Let's continue with the orbit and constellation description. This is a map of prone to vector-borne disease areas in the world. And our aim is to observing and gathering data from these areas. And here you can see our orbits. As I mentioned before, we have 3 orbits, and you can see that our orbits are perfectly covering this area, which are because they designed for them. And here you can see an animation of one of our orbits. And the other two orbits are the shifted versions of this orbit. You may ask, you are using 6 CubeSats, why not 10, why not 20? While we are planning our mission, we try to reduce the cost and higher the efficiency. And considering the revisit time, 6 satellites is enough and perfect for us. To continue with implementation plan, we are planning to work with World Meteorological Organization, World Health Organization, and Turkish Space Agency. With the help of Turkish Space Agency, we are planning to protect our world from any other vector-borne disease. And here you can see our main mission risks and estimated total cost without launch and operation costs.
This is the end of our presentation. Thank you to our university, our sponsor company, Planes, our advisor, Associate Professor Dr. Halil Arsi Söken, and Cansu Yıldırım and Semra Sultan Uzun from the winner team of MIC7. Thank you for listening.
Okay, thank you very much.
Thank you for the presentation. Vector-borne diseases are normally spread by insects like mosquitoes. But if you take COVID as an example, COVID was spread by humans, by people, not by the environment or the wind or the rain. So I think a constellation of satellites will not help you to detect the spread of COVID, for example. Do you agree or not?
Yeah, that's right. This is actually really interesting research. That research was made in a specific area in Angola, and that was the further investigation will help us to detect and predict the diseases, not just for vector-borne diseases, the other diseases too. So
Malaria,
maybe in the future, COVID may be not a risk for us with the help of the satellites. So it needs a further investigation. And as I said before, the researches in this area are not explored yet.
Just a final question from me. How can SAR help you to detect temperature? It's a bit, I don't understand how SAR images can help you to detect temperature variations.
Are you saying that detect the temperature exactly?
The temperature on the ground. How can SAR measure temperature on the ground?
Okay.
Infrared cameras can measure temperature on the ground, but that's not a radar images.
That's why we have 2 different satellites working as pairs. I mean, in one orbit, one active and one passive satellites will operate together. And you can think like one is detecting the temperature exactly, and one detects the spread of it, distribution of it, sorry.
Yeah, but you listed there under SAR that temperature specifically can be measured by SAR images.
We must made a mistake, we're sorry.
Yeah, I have a very similar question. So why you use the SAR and the image for detection of such kind of the vector-borne diseases? For example, if you put some in situ sensors like a temperature sensor, humidity sensor, precipitation sensor, and other sensor on the ground, and if the satellite collect the ground information by using the RF and so on, that would be more effective to show detect the environmental change. So I think I'm not sure why you use this kind of the SAR and the image sensor for detection of the.
Yes, we needed an active remote sensing sensor, and when I was searching for it, I came across with SAR because it can detect cloud coverage and topography, and we need topography for measure the wet zones, and SAR is a perfect sensor for us. That's why we choose SAR. Thank you.
Yeah, okay, thank you very much. So the SAR can, obtain all the required information.
Excuse me?
Yeah.
Can you repeat it?
Yeah, SAR synthetic aperture radar can, obtain all the required information.
Yeah. Thank you.
Yeah, very similar question. Yeah. Similar question. Yeah. How do you utilize the data set from the two satellites? Maybe you will use the data combination of two satellites, but how is the data sample or something interval of two data set or something like that?
So if I'm wrong, please correct me. You're asking that how would you analyze the data when there are too many satellites?
Maybe you will use the two combination of data, but you will get these two data, maybe the separate data set and a separate time.
Okay. The thing is, all the data, as I mentioned before, are being sent to master ground station, and you know that the more data is better for AI to educate itself, and that's why we use so many data and the other data too.
Thank you. You will find out some kind of hint for the variation from the many data, maybe from the.
Yeah. It can be said like. Thank you so much for your question.
A question about your constellation management. You said that it will be done by the ADCS system without any propulsion. Can you explain to me?
Yes. We don't have any propulsion system, and if you like, we can show our ADCS system in appendix. Appendix, please. We don't need any propulsion because the launcher will deploy the satellites in orbits directly, and it doesn't have to be like upper or lower its altitude, and we are using the ready ADCS systems to provide them faster. If there is any like shifting or failing, they can be replaced easier.
Yeah, but your satellites, even if they're in the same orbit, if they just have different attitudes, they will have different drag, and then they will drift apart or they will drift closer to each other. So that management of the constellation, how are you going to do that?
We thought about propulsion, as you said, but if we add propulsion, the size increases and the budget also increases. So our aim is like more sustainable constellation, and to do this, we think that maybe we can increase the satellites number and lower the cost of it, so we can replace it easily.
How will you deorbit your satellites after 5 years?
It's like 5 years later, they dispose themselves. Like 5 years due to drag or something, their life cycle is like 4.5 and 5 years.
Yeah, but that something must be specified. You must design for it. They will not deorbit themselves from 500 kilometers. They will stay there for 25, 30 years before they deorbit. So you have to do something to deorbit the satellites quicker, sooner than 5 years.
Okay, we will consider about it and ask our advisor too. Thank you for your consideration.
So at the moment, you're launching into 2 different inclinations, which requires 2 launch vehicles. And there's not that much difference between the 2 inclinations. So I'm wondering if you've considered launching into some kind of intermediate inclination, and therefore you could only use 1 launch vehicle instead of 2. What do you think about that?
The only difference in our orbits is the right angle of ascending nodes. All the inclinations are the same. Maybe there's a mistake in the figure, but the thing is, only the difference is the right angle of ascending node.
Inclination. One of the inclination is different. It's right because there was its change after the second report. The change is therefore to cover more wide range of the Earth, if you look for the vector-borne disease data, there are some regions that we don't cover with the smaller inclination, and we want to put it as redundant also. Yeah.
Sorry for my answer.
Okay, I think we have to stop here. Thank you very much, team.
Thank you so much. Thank you for your attention.
Okay, the last presentation is a video presentation from Italy. The name is Cross Eye by Francesca Pelliccia from Naples.
Good afternoon, I'm Francesca Pelliccia, and I'm here to present CrossEye, a CubeSat LEO constellation for plastic litter detection in open sea. Every year, 40 million metric tons of plastic enter river, lakes, sea, becoming one of the main sources of pollution. All around the world, there are some garbage patches. There are hotspots in terms of plastic accumulation. And the starting point of our mission was what we can do from space. In particular, for plastic litter detection from space, several technologies can be considered. On one hand, multispectral imagery, hyperspectral sensing, and GNSS reflectometry, that are technologies that have been demonstrated good capabilities in this field, but actually there are no global, no operational system for global monitoring detection of plastics with sufficient temporal and spatial coverage. On the other hand, there is SAR imagery. SAR, with these unique capabilities in terms of all-weather, all-time capabilities, will allow global monitoring of plastic litter at sea, but now there are no robust approaches for SAR-based plastic detection at sea, since there are no assessed dataset to train and test new procedures or large scales. So, with the idea of merging both the strength points of this technology, the CrossEye combined in pendulum remote observation CubeSat system for ISI mission concept was born. In particular, the mission objectives are listed here. We can start with the macroplastic detection in open sea through electro-optical acquisition. The second main mission objective is the validation of this new measurement principle based on electro-optical SAR technologies, and then development of a database of collected plastic data. Also, the key parameters of the system are listed here in terms of the minimum spatial resolution is required for plastic litter detection, the bands in which the payload has to work, the 6 bands from near to SWIR in order to properly compute the indexes, normalized different vegetation index, floating debris index, and floating algae index. And also one key parameter about the condition of the acquisition, in particular the acquisition between these technologies has to be simultaneous. Meaning that we can accept a time lag of more or less 4 hours. The mission concept, CrossEye mission concept, can be summarized through this workflow in which we can see 2 inputs that are the electro-optical images and the SAR images. With the early images, it's possible to compute the indexes FTI and DPI in order to build the ground truth, so to detect the plastics in images. On the other end, we have SAR images, and from the comparison of these 2 inputs, it's possible to properly train the artificial intelligence algorithm that can then allow the independent acquisition and detection from SAR of plastics. In particular, this comparison have to meet some requirements. The images have to be acquired over the same areas with a limited temporal distance. This leads to the concept of pendulum formation in terms of orbit design. In particular, considering one couple, one CrossEye and one ISI satellite, it's possible to appreciate here the overlap of these SWOTs, the SWOT of the 2 technologies, the payload, that it's possible thanks to the design of a pendulum formation in which, starting from the initial orbit parameter of ISI, CrossEye orbit plane is properly defined, considering some deltas in right ascension, eccentricity, and true anomaly. In particular, these deltas in the orbit parameters provides the radial cross-track and a long-track separation that are needed in order to identify a safe ellipse in which CrossEye satellite can move with respect to ISI without collisions. So, considering the total space segment of our mission, we have a constellation in which we can identify 3 main orbit planes, so 3 main different local time and the assembly node, range of altitudes, and also inclination, thanks to the deltas in the orbit parameters for each couple of the constellation. As for the ground segment, 11 of 17 actively spaced ground stations placed in mid-latitudes have been chosen. In particular, it's important to underline that the link between these 2 missions, ICE and CrossEye, is possible at ground segment level, since in this case it's important to have the possibility to compare the products, so the images from EO payload and also SAR payload, so the 2 ground segments have to communicate. Since there are some fast detection requirements that have to be met, and also some standard compatibility requirements in terms of standard 6U CubeSat platform, so in terms of mass and power constraint, a custom electro-optical payload have been designed. In this case, we can merge these 2 payload technology, veneer to sphere, in order to have 1 single payload on board a 6U CubeSat platform with a mass of more or less 4 kilograms. So, considering just 1 payload that is custom and all the other components of the subsystem that are components of the shelf, it's possible to obtain a preliminary design of our platform, for which in this case we can appreciate the mass budget and also the total average power consumption. So, with these numbers, we can say that this preliminary design shows the compatibility of our platform with a 6U standard platform. As for the risks of the mission, some risks about payload, the formation, the database, the failure, and also management have been considered. In particular, a particular attention is to properly consider for the payload and the formation that are critical both in terms of impact and also likelihood of the risk. So, in conclusion, we can say that the CrossEye platform design is feasible, integrating all components of the shelf except for the payload that is custom. The design is easily adaptable to other SAR-equipped platforms. In this case, we have considered ICE, but this is possible for the constellation. In general, an incremental strategy, in fact, of CrossEye mission is possible in order to widen the quantity and the quality of all the collected data. So, it's also possible to underline the capability to build a database that can be tailored to fit the customs demands for a particular application. And also, it's important to underline the contribution to plastic litter detection from space, promoting sustainability and furthering the understanding of Earth ecosystem. Thank you for the attention.
Okay, that was very quick, so you will have more time to ask questions if you like to.
Your mission is very much linked to ICE. Have you spoken to the ICE people? Because I imagine they've got other goals for their SAR satellites. Are they willing to assist you and to generate data that you can process with the CrossEye data that you're going to generate with your satellites? What is your link with ICE? Have you spoken to them about your mission?
Okay, in general, the mission concept has been conceived considering that our design and our platform and also our constellation has to be adaptable with respect to the constellation with which we want to collaborate.
Please,
in general,
if you are, Francesca, if you are in the same room, please mute other computers.
Yes, sorry. Okay, so in general, we have conceived our mission concept in which our platform and in general our constellation is to be suitable to work with other constellations that are already in orbit. As I already said for the presentation, our link with other missions is possible at the ground segment level. Also because we want to imagine a simple mission in which there are no links in terms of flight control dynamics in general in orbit, because in this case the control and also the design of the platform will be much more difficult and tricky.
So in general, the idea is that we have to communicate at the ground segment level. So we know which is our ground segment. For our case, we have decided to select lead space, but there are also other ground segments that we can select. And on the other hand, we have to collaborate with another ground segment that is the one that is mission dedicated with respect to the constellation that we have selected. And in this case, we have to know in a precise way when the acquisition of the payload, in this case, the SAR payload of ISI starts, when it ends, because we want a perfect synchronization that is required for the pendulum formation, because the concept of our mission works if and only if the comparison between the products is useful. And it's, in this case, the requirements of image over the same area and also time lag of more or less 4 hours is possible only if we have this connection at ground segment level. So in general, this is adaptable with respect to the mission that we want to collaborate with.
Your ground sampling distance.
If I can add on something. We also, we also communicated through means of ESA with ISI, because we participated into different workshops, and in particular we also took part into flyer satellites, so they know.
Your ground sampling distance for your multispectral camera is 20 meters. How do you think you can see plastic floating in the sea? Or are you only planning to see plastic patches that covers a big area? Because there's no plastic bottle that's 20 meters in diameter.
Okay, in general, the requirements about the minimum spatial resolution that is required to detect plastics is more complex than just the requirements that is related to the physical dimensions of the patches. This means that after an in-depth study about the literature and also the capabilities and the potentials of the electro-optical payload that are in orbit, for example, the multispectral instrument of Sentinel, just to consider this reference satellite, we have studied that it's possible with this resolution to detect plastics because we are not considering physical dimensions of garbage patches of agglomerates of plastics. In general, we are talking about plastic concentration. So it's just a matter of density of that material in the open ocean in this case. So in general, after our studies, we have concluded that it's enough to consider 20 meters because we are, in reality, actually, we are not considered the real garbage patches, but we are talking about concentrations. And it's also possible to find some maps in which there are density hotspot accumulations so that, for example, also other agencies have been considered. And in general, we can see some maps in which there are concentrations and not just the real plastic island or something like this.
Okay, so thank you very much. So you said you will use machine learning for the processing, and so how you can get training data? That means training data will include some ground truth data. So how you can get a ground truth data? Because it's very hard to find such kind of the data on the oceans.
Yes, the idea is that in general, the satellites that are AO payload equipped, so for example with push broom scanners or something like this, actually are ready to detect plastics because through the computation of some indexes, as already said, for example, the normal difference vegetation index or floating debris index, it's possible having some images to compute this index and find in general some concentration of plastics discriminating between different materials in electro-optical images. So in general, the potential of electro-optical images to see plastics is validated, and in general, instruments like the multispectral push-pull or other instruments, also hyperspectral cameras and so on, are able, in general, to see plastics through the computation of these indexes, and so also able to allow us to build a real ground truth of these images. But in general, there are no operational systems that actually are doing this for mission interests, space economy, and also other reasons. But in general, the idea is that in this case, the potential is validated, but also considering the motion of, for example, the atmosphere and also the concentration of clouds and the relation between the motion of plastics and so the characteristic motion of in open oceans, so of water in general, and the motions of the atmosphere, so the capabilities of some sensor to see also through clouds or with particular illumination condition leads to condition in which there are no operational systems that are able to do this. So in general, both for mission interests and objectives, and also for the complications in the plastic detection to this instrument, it's not possible to have already today a ground truth that is ready to train the artificial intelligence, but the idea is that it's possible to do this, and we want to do this. And on the other end, we have the SAR technology, because there are, in this case, we have, there are no the limitations of the electro-optical payloads. So, for example, a SAR can work in all weather or time capabilities. It's more suitable to find and, in general, to follow the motion of the plastics in general, because we have no limitations in terms of configuration of acquisitions. So in general, it's possible to merge this technology, because the idea is to have no limitation in acquisitions to train the artificial intelligence with too much data in general.
In your AI training process model, there's a feedback to the SAR images. So I wonder, is that feedback there for the AI training, for the AI to act on those images, or are you feeding back to change the processing on board or the way you acquire the images?
Maybe we can consider also a no feedback in this case in our chain for the mission concept. So in general, we are in two separate lines, and then considering the images that are ready to be compared, maybe it's possible to do the training.
So you plan to use SAR as an alternative to optical imaging for identifying ocean plastics. Have you checked whether... No. Oh, sorry.
Sorry.
So that's the
no,
goal, right?
It's not a matter of alternative or options. In general, we need both the technologies. So we need both the input to train the artificial intelligence, and this is the reason why we have to consider a particular orbit formation to achieve this condition. Because if we have some conditions in which the orbits never intersect in terms of swath width and so covered areas, for us, it's not possible to train artificial intelligence, because we can have the overlap of the images acquired over the same area. So the idea is that over the same area, for example, knowing in a precise way the acquisition time, the start acquisition time, the end acquisition time, and the coordinates of the satellite, it's possible to acquire the same image with two different payloads at the same geographical area, so a target area of interest, and then compare these two images, considering that on one end with the electro-optical, it's possible to see plastics in an operative way. On the other hand, SAR is not able to detect in an autonomous way plastics. So in general, we have to compare these two products, train the artificial intelligence, and then once the artificial intelligence is properly trained, after a lot of months and also images that have been acquired, the artificial intelligence will be able to say to the SAR, the synthetic aperture radar, in which images if it's possible plastics are present. So in general, this means that the artificial intelligence can allow the independent acquisition of the synthetic aperture radar once it's properly trained.
Yeah, thank you. And so have you made any kind of concept studies or rough image comparisons between SAR and optical, even at this stage, to check the proof of concept? Because maybe there's a risk that even after training the data, even after you've obtained the trained model, it still can't identify plastics. So have you tried to make a proof of concept?
Yes, we are working on this because actually we are not a proof of concept, but we have two separate lines in which we have some images, for example, the one generated by the multispectral imagery of Sentinel. And on the other hand, we have other study in which, for example, we can see a potential acquisition of plastics in SAR image. So we have two different lines. Actually, there are two separated lines in this moment. But we are working on this proof of concept because we believe that can work very well.
Okay, thank you very much. We have to stop here.
Okay, thank you.
Thank you very much, team. So now we are going to have a 15 minutes break. Please be back at 17:35. We have two nice presentations by the sponsoring company iSpace on challenges, or let's say challenges for a private company for a lunar mission. We are looking forward to your speech. Okay. Yes, after your presentation. I know. So it's not here. No, I mean, but the presentation, I think it's still here, no? Let me ask. I thought we continue here. Then after this, yes, we go to the other presentation. Okay.
Go to the stage together.
Okay, sure.
One by one, but
All together, yes. Yes, okay, no problem. No, sorry. I didn't understand. Okay. Yes, there is the photo session. Yes, here, with everyone. Hello, ladies and gentlemen. Please take your seats. We are starting with the last session for today, the supporting company presentation. We have Masayuki Urata and Ertan Ümit from iSpace. And please, floor is yours.
Okay, good afternoon. So I'm Masayuki from iSpace Japan. So nice to meet you. And first of all, we would like to express sincere appreciation to UNISEC to have such great opportunity. And actually, iSpace joined UNISEC as a corporate member this September, very recently. And so we came to know that UNISEC is doing such great activities. And now we would like to contribute to UNISEC members to realize potential missions. So this is our like aspiration. Yeah. And today we listened to the finalist presentation, and we are very impressed, and we are very happy that the two of the teams gave a presentation related to lunar mission. So we are so excited. So thank you very much. Yeah. So today we would like to explain about our company, our business. But before that, so I would like to ask you one question. So have you ever been involved in the lunar missions? So if you have experience in lunar missions, so could you raise your hand? Oh, 1, 2. Yeah, thank you very much. So I can see, so not so many people are actually involved in the lunar missions. But so iSpace has a vision of Moon Valley 2040. So we are declaring that in 2040, there will be 1,000 people living on the lunar surface, and 10,000 people will be traveling between the Earth and the Moon. So maybe it sounds very challenging, so it can be or something. But we would like to keep saying like this to promote so lunar missions and also creating a lunar industry as well. So from a point of view of like a private sectors. Yeah. Then before going to the company presentation, so I would like to pass the ball to Mr. Ertan Ümit. So actually, so he's our colleague from Luxembourg office. So he's from Turkey, and he was like a winner of past UNISEC mission idea contest. And I would like to ask him to explain about his like educational background, a story about mission idea contest, and also his career path as well. So, Mr. Ertan, so please kindly.
Thank you very much. Hello, everyone. Congratulations to all the teams. Again, the presentations and projects were really, really interesting. I hope the juries will go easy on you, and may the best one win. So I'd like to thank Ray-san for inviting me to present some history about me. Is that? Okay. Sorry, that's the remote. So I would like to talk a bit about me and my career, to show how relevant MIC is for all the future students, where like 10 years ago, where I participated MIC and how it affected my career in general. I have my bachelor degree in electronics engineering and software engineering, and then my master's degrees in aerospace engineering in Istanbul Technical University, where I worked on several CubeSat missions, where CubeSats were like beginning to kick off, where you saw, like you saw in the presentations early today from Professor Nakasuka. We started, so I have worked on 3 CubeSats, starting with ITU PSAT-1, which was the first 1U CubeSat, quite simple design. I'm afraid to say anything bad because the professor is actually there on the corner watching me. Thank you, Professor Aslan, for the opportunity. It's still operating. It's really successful. How many years again? 14 years. Yeah. So I worked on that project. Then I moved to. I worked 1 year in the Delphi Next project, which was a 3U CubeSat. Then I get back to Istanbul Technical University, and we worked on the TrueSat UCuSat project, which is again 3U CubeSat, as you see here. These were all university level interesting projects. Then I moved on to Belgium to work on a project called Karman on Von Karman Institute. This is again a 3U CubeSat. It's slightly unconventional. The main mission was to survive re-entry. So we had two missions. One was to do orbital operation and orbital maneuvering through drag changes. And then the second and the main objective was to survive the re-entry. Here you can see this is a test sample that we did in our own test facility where we simulated the re-entry plasma. And this left one is tested in Cira facilities in Italy, where the biggest re-entry test facility in the world happens. And this is historically the first time one-to-one scale test subject was tested for re-entry. Yeah, you can see me there also, still young and ambitious. And this is also me presenting that mission on PRIMIC 4, and I actually won the award. The same jury, or mostly similar jury, awarded me, and you can see Professor Nakazuka. He wished me all the luck, and by all this motivation, we managed to launch the satellite. It re-entered, I think, a couple of years ago, but we were unsuccessful to retrieve any re-entry data from it. The orbital operations were quite successful for some time. Then, after that CubeSat and in general MIG, I start working on the ExoMars project, where where I was working for the LARA instrument on ExoMars. I was thinking that back in the day that I was moving away from CubeSats. I didn't realize, but if you look closely enough, the instrument looks like a 3U CubeSat itself. And these three antennas actually look like reaction wheels. I just realized that when I was preparing this presentation. The goal of that project was to have a direct Mars to Earth communication, and then to measure the perturbations on the Mars rotation. Through that, the scientists were planning to measure different planetary interior modeling. I was supporting with the instrumentation activities. And afterwards, quite recently, I would say, I started working for iSpace, where we, in Luxembourg office, we are developing the rover. And also I realized this quite recently. If you look a bit from a distance, this also looks like a 3U CubeSat with wheels attached. So yeah, if you're coming from CubeSat world, everything looks like a CubeSat basically. And here's our lander. I'm sure Rota-san will have more details, and hopefully you will see quite a lot more information about that mission in the future. Yeah, I Currently, I work as a payload system engineer where I support proposals and customers and payloads on different challenges, trying to help them for a successful mission return. And yeah, you can see in my career path that mission idea contest was like a key parameter where we see the 3 dB bandwidth actually sits. Yeah, and hopefully from now on we will see a lot going on the moon. So thank you very much.
Thank you very much, Mr. Eltan. And let me continue our company presentation. Yeah. Okay. Yeah. So as I told you in the beginning, so our long-term vision is Moon Valley 2040. Yeah. So we would like to create industries or market on the lunar surface. Yeah. Then it is well known by you, but why Moon is interesting from point of view of industry or commercialization. So it is because of the water resources. So according to the recent research, so there are abundant of the water resources on the lunar surface. And if we can extract such water resources and separate to the hydrogen and oxygen, we may make propellant. Yeah. Then due to the low gravity, so it will be more cost efficient to provide such propellant to like a deep space missions or even to low Earth orbit satellites. So this is like our target. Then this is our corporate information. So our company was established around 13 years ago. 2010 September. Our company began as a rover development company. Yeah. And currently, so we are developing lunar lander and lunar rover both. Yeah. So we have around 270 employees and from 27 nationalities. So we are very global. And more than half of them are engineers. Yeah, we have 3 offices, headquarters in Tokyo and Europe office. So Eltan is from Luxembourg office, mainly developing lunar rover, and also Denver office. So they are developing next series of lunar lander. Yeah. As for the financial track record, we have raised around $300 million US so far, including our IPO in this April. So as for IPO, so it was the first IPO in Japan as a space startup. Yeah. As for our business, so we are providing mainly 3 services. So first one is payload service, second one is data service, third one is partnership service. Payload service is like a logistics. So we provide logistics service. So we will deliver a customer's payload to the lunar orbit or lunar surface. But in addition to that, we will provide, of course, so power, communications, or thermal conditions together. As for data service, of course, so we will equip many sensors on the lander and the rover and collect like environmental data of lunar surface or lunar orbit. And we would like to utilize such data to the end users. Third one is partnership service. It is like a Formula One, some partners, logos. So we receive many supports from our sponsors. Yeah. As you may know, so we tried first mission last year. So we launched our first lander. And let me show some video.
3, 2, 1, ignition.
So actually, so we launched this first mission lander last December, and it took around 4 months to reach to the moon. Yeah. Then this is the photo taken from the lunar orbit using our in-house camera. Yeah. So before trying this mission, so many people told us, so you have good dream or great dream, but we proved that we are capable to reach to the lunar orbit and take such pictures as a private company. Yeah, and this is also some movies. So like from that 100 kilometers height, yeah, in orbit. Yeah, then as you may know, so we tried lunar landing attempt last April, and unfortunately, so it was incompleted due to the software error. So the lander ran out of the fuel at the 5,000 meters above the lunar surface. But I thought unfortunate, but fortunately, so, and most important point is we identified the root cause. So we found out that this is software error, so related to the altitude measurement. And we confirmed there was no hardware error. So we used we proved or we confirmed the capability of our hardware, and also we will improve our software for the mission 2. Then for your information, so we are going to launch next mission next year, 2024, in the winter. Yeah, then we are going to bring our own rover as well, and developed by Mr. Elton. Yeah. As for the mission 2 payloads, so there are several payloads, like Takasago thermal engineering, water splitting experimental device, and also Euglena's like a microbes experimental device. And also, I would like to mention that there's one mission from National Central University in Taiwan. So they are also team of UNISEC. So they are member of the UNISEC, and we are proud that we are going to deliver their payload to the moon. Yeah. Then this is our rover's description. So our rover is, as Elton mentioned, like a 3U CubeSat, not so big, so like a 5 kilogram mass, and there is a 1 kilogram payload capacity to be mounted, that red squares part, and to be deployed to the lunar surface. Yeah. Then as for the further mission, so we are already planning mission 3 to be launched in 2026. So we are going to upgrade the lander. So as for the lander used for mission 1 and mission 2, the payload capacity was or is 30 kilograms. But as for the lander for mission 3 afterwards, so it has 300 kilograms payload capacity, so 10 times bigger than the before. Then actually it is like a commercialized lander. Then as for mission 3, so we already got contract from NASA under the CLPS, so Commercial Lunar Payload Service Program, and we decided to bring around 95 kilograms of NASA payload. And also interesting point is landing location will be far side of the moon, so Schrödinger Basin. And in order to keep communication between the Earth and the far side of the moon, we are going to bring 2 relay satellites together with this lander. So the most important point is, so as a commercial company, private company, our intention is to realize continuous missions, so once per year or multiple times per year in the future. It is very important, and it will provide opportunities to you or some other organizations more opportunities to try lunar missions. Yeah. Then we would like to say is, so let's go to the moon together. So in the future, so we are expecting to collaborate together and realize a mission together. So it's a little bit earlier, but we would like to finish the presentation. So thank you very much.
Thank you very much for enlightening presentation. Way to the moon, interesting. Okay. I think now, where is our Secretary General? Kawashima-san? Yes. So anyway, next step is the award ceremony and photo session. So we have to wait for the jury to come and make the announcements for the winners. So I think, well, yes. We have 9 minutes. You can rest for 9 minutes. Then, okay, since most of you are contestants, you will be here anyway, so. Okay.
Okay, so please get seated. So let us start award ceremony. Thank you very much. Now I would like to announce the recipient of each award. The first one is the IAA award, and the second one is a student award, and the third one is a second prize. And finally, I'd like to announce the first prize. It's okay? So maybe the presenter will be very nervous now. Okay, so let us start the award ceremony. The first three, I'd like to announce IAA award. Okay? IAA award goes to, please show. Oh, Masashi Kamogawa, University of Shizuoka, Japan. Congratulations. Kamogawa-san, please come up the stage. And the presenter is Max. Yeah.
Okay. So Kamogawa Sensei, I would like to present to you this IAA award to Kosuke Kanda, Kyogo Otani, Reiji Kobayashi, Tomoyuki Ida, Masahiko Yamazaki, and Masashi Kamogawa from Nihon University and University of Shizuoka, Japan, for the paper entitled CubeSat Constellation-Based Global Early Warning Tsunami Forecasting on the occasion of the 9th UNISEC-Global Meeting, November 29, 2023, Nihonbashi, Tokyo, Japan, on behalf of Professor Hermann Stein and Professor Shinichi Nakasuka. Congratulations. Would you have any reactions to this award that you would like to share with us?
It is very honor. I'm very happy to get this IAA prize. Thank you very much. Thank you very much.
Yeah, thank you. Thank you very much. So next, I'd like to move on to the student award. Okay, student prize goes to, Nepal team. Congratulations. Nepal team in the online. Congratulations. So the Ueno Sensei, gives the certificate.
Okay, congratulations again, and you have the student prize. Team from the sorry, this is very difficult to pronounce. Tribhuvan University, Nepal is okay, and the member is Bana Pokal. Or no? Vivek Yonzan and Simon Chris Ramishane and Sudit Batalai. Sorry, maybe it's not correct. And the working title is monitoring the greenhouse gas on the time on the continental collision plates and warning system of glaciers. Okay. Zeros over the Hindu Himalayan range, and this is very, very urgent target, and also realize three combination of satellite very efficient way. Very nice idea. Thank you, and congratulations.
Thank you. And the student prize has only this prize can get some money. And so please present that also the Nepal team.
Okay, this is your certification and some prize. And maybe this will be transfer your site from this office. Okay, please wait.
It's a very big money. Congratulations.
Thank you.
So the Nepal team, could you give us some comments from your side?
We would like to thank our mentors, Sudeep sir, Avas sir, Kamal sir, all the peeps at the Antaraksya Pratishthan Nepal were there with our journey. So yes, thank you all of you, UNISEC, MIC, for giving us this opportunity. Yes, thank you.
Thank you very much. Yeah, please continue your effort and actually develop the satellites in the future. Thank you very much. Now, let's move on to the second place. Okay, second place award goes to South Africa team. Congratulations. So Richard will present the certificate.
So we've found that this presentation and this idea was not just technically interesting and technically valuable, but also valuable to the contribution to society, the impact in society in a global way, and to safety of life. Second place is awarded to Dirk Schlaber, Tian Killier, Lauren Cook, Jürgen van der Merwe, Saad Badat, Michaela Isbeck, Philip Lutreet, Rowan Twiley, Dr. Arno Bernard, Dr. Willem Jordan from Stellenbosch University, South Africa, for the paper entitled LEO Backup Earth Navigation System, LEO Beams, a phased array Ka-band CubeSat constellation PNT solution for the goal of increased reliability. On the occasion of the 9th UNISEC-Global meeting, November 29th, 2023, Nihonbashi, Tokyo, Japan, by Herman Stein and Shinichi Nakasuka. Congratulations. You have some comments?
Okay, so please give us some words.
Thank you, everyone. Thank you for the prize. And just on behalf of all the rest of my team, I'd like to thank all of them as well for the hard work that they put in and their contributions. Thank you.
Thank you. Okay, so now it's time to announce the final one. First place. Okay? Are you ready? First place of this year's Mission Idea Contest 8 will goes to University of Rome Sapienza team. Congratulations. Chairperson of the judge, how much time will give the certificate?
To these lovely ladies, this first prize is really something. It was a very close competition, I must say, and one of the goals of UNISEC is to go to the moon and beyond, and you've demonstrated that with your mission, going to the moon and do some excellent measurements, and that is of importance on the moon. So now I have to name all the team members. My Italian is not that good, so I hope my pronunciation will be good enough. Michaela Boschia, Valentina Abignale, Gabriela Agresti, Charlotta Amicone, Eleonora Casaselli, Lorenzo Chavari, Chiara De Maria, Alessia Di Giacomo, Angelo Fabrizi, Chiara Falcone, Maria Carla Fiorella, Carolina Guinea, Siddhant Kumar, Gaia Lorenzi, Lorenzo Mazzetti, Linda Mesticola, Alessandro Moretti, Asia Nicolai, Alessandro Piru, Angela Raffaele, Leonardo Scardella from Sapienza University of Rome, Italy. And the paper Moths, Moon Observations Through Hyperspectral Satellites, a 6U lunar CubeSat constellation for the observation and analysis of transient lunar phenomena. On the occasion of this 9th UNISEC-Global meeting, today's date, and given by me and Professor Shinichi Nakasuka. Congratulations to you.
Okay, so would you please give us some words?
I want to thank all the jury for this first prize. I want to thank all the team that works on this project. You see, we were a lot of people from Sapienza University of Rome, and I want also to thank our professor, Paolo Marzioli and Fabrizio Virgentili. Thank you so much.
Thank you very much. And now we'd like to, present the certificate of the finalists to all the members of each team. So all the members, please come up to this stage. And also the jury, please come up. So the jury will give the certificates of the finalists to each team. So the first one is Haman.
Yeah, the certificates for Sapienza University in Rome, Italy. So I hand out, because there's many names on this certificate list, and you can give the certificates to everyone at your university. Congratulations again.
To Stellenbosch University and the associates there, I'd like to say congratulations, very lekker.
So I've already given my certificates to Kamogawa Sensei, but just to reiterate, we really enjoyed the kind of out-of-the-box idea. So congratulations again to your team, and we're looking forward to the next phase of your project. Congratulations.
So the Nepal team is not here, and so we will send. Okay, so the next is Romania team. Okay, so David Emmanuel Tursi, Rasmus Mihali Parade, Robert Andrei Dinu, Andrea Elena Braga, and Maria Alexander Dolbe from Polytechnica Bucharest National University for Science and Technology, Romania. So congratulations, this is a certificate for the finalists. Thank you very much. And the next one is a Thailand team. Please come up, Thailand team. Yeah, Chayapat Songpiat, Chilasu Swetrong, Kitty Prof, Fancha Chat, Longfong, Dunda Akunit, Nuti Luku. It's very difficult to pronounce. I'm very sorry. Sri Dugra, Ponsapak, Lakumot, and Parames, I'm Lalong, Satesit, Sagalung, Tirawat, Pitu Supon. So this is the certificate for the finalist. Congratulations. Yeah. continuous effort. Thank you. Final one is a Turkish team. Okay. Yeah. Alpa, Güvercin, Duru, Seren, Serit, İpek, Olmets, Yunus, Emre, Ozdemir from Middle East Technical University, Turkey. Congratulations. Thank you very much. So now everything is finished? You get everything? Okay, so now we'd like to conclude this year's Mission Idea Contest 8. And before closing that, we would like to pre-announce the next year's Mission Idea Contest from Lake Kawashima.
Okay. So, congratulations, everybody. And I'm very, very proud of all the people here and all the people to listen to that wonderful presentation. So next year, we are going to organize a Mission Idea Contest for Moon. So Lunar Mission Idea Contest. We will organize it, and the venue will be South Africa. So please start working on lunar mission. The detail, the criteria or other things will be discussed later, but just a study about lunar mission and the moon condition and other things too. So we will make a photo session after conclusion, so please stay here, okay? And the UNISEC members, please stay here, because you guys will be come here and take a photo together, okay? So thank you very much. Maybe you should conclude.
Yeah, you should.
Okay. I'm reserved. Okay, okay. All right, thank you very much. And today we'll have a reception at the Cross Nihonbashi Tower. So if you wanna come, please join us. If you have not registered, let's see. We'll just let me know. We'll take care of that. But it is a very good reception and the good energy. I'm just feeling very good energy now. And I hope you also feel the good energy. And good energy is encouraging, motivating, and inspiring, and very warm and loving. Thank you very much. So let's go to the moon next year.
Okay. So thank you very much for attending this session. And now we'd like to conclude. We'd like to close today this year's Mission Idea Contest 8. And finally, please give the big hand to them. Congratulations. Thank you very much.
All right, we're gonna take the first shooting. He's the guy with the shooter, okay? And everybody, it's you can come up to the stage, please. Okay. Ah, so. All right, and then Zoom member. Also, you guys on the screen. So everybody smile, please. Some guy walking. It's hard to show a smile, but yeah, it's great, great smile. Yeah, in outside. Yes, great, great. Okay, here's the super camera guy there. You need to show this great, great smile because you guys next year are gonna be to the moon. So let's make the rocket smile. Oh yeah, too much. It's good height, yeah. これ逃げちゃおうかな。逃げちゃおうかな。あ、あ、いやいやいや。So we give you enough time to make a great smile. So now practice, yeah. It's okay. And everybody can see that this guy, the lens. If you see the lens, you can show smile. Yeah, you can. Oh yeah. Just wait. もういいかな。大丈夫でしょうか? Is it okay to the changing? 杉田さん Okay for that? ちょい待ち? ちょい待ち means just a moment. In Japanese slang. Oh, everybody looks like, very serious. So, what happened? It's okay for that? Well, already you taking it. So everyone smile, yeah. Smile for now. Yeah. Fire. It's great. Smile. And make some pose. You gonna? Second time. Second time. First time is very, looks great. Okay. 硬い。everybody stiff, like,はい、スマイルね。じゃあ、ポーズ、yeah. Yeah, to the right fist. Go to the moon, yes, okay? Go to the moon. We'd like to go to the moon. Mars, Neptune. It's already. One more, sorry there. Go to the moon. ニューヨークに行きたいか。ありがとうございました。Thank you, everybody. Thank you for the Zooms, guys. It's done. Thank you. Thank you so much.
、レセプションに行かれる方は、クロス日本橋タワーの7階にお越しください。Please come to Cross 日本橋 Tower, 7th floor. We'll have a reception.